The Fibonacci sequence is one of the most fascinating mathematical patterns found in nature, art, and architecture. This sequence starts with the numbers 0 and 1. Each subsequent number in this series is generated by adding the two previous numbers. So, after 0 and 1, the next number is 1, then 2, then 3, followed by 5, 8, 13, 21, and so on. The pattern continues infinitely, producing an ever-growing series of numbers. Many marvels of the natural world can be modeled by this sequence. For example, consider a sunflower's seed head. The seeds are arranged in spirals that can usually be counted in Fibonacci numbers. This arrangement allows for the optimal packing of the seeds, maximizing their growth and exposure to sunlight. Pine cones and pineapples also exhibit this pattern in the form of spirals, further showcasing the beauty of Fibonacci's numbers in nature. Apart from plants, Fibonacci numbers also appear in the animal kingdom. Take, for instance, the reproduction of rabbits. In the famous thought experiment posed by Leonardo of Pisa, known as Fibonacci, he imagined a scenario where each pair of rabbits produces another pair every month after reaching maturity. The number of rabbit pairs can also be delineated by the Fibonacci sequence: one pair in the first month, another pair in the second, and so on. As we peer deeper into the intricacies of nature, we find the Fibonacci sequence in the structure of certain shells, such as the nautilus. The growth pattern of this marine mollusk resembles a spiral, repeatedly expanding outward in a manner consistent with Fibonacci numbers. This is known as a logarithmic spiral, and it is both beautiful and efficient. In addition to its occurrence in nature, the Fibonacci sequence has influenced the realm of art throughout history. Artists have often used this mathematical principle to create works that are pleasing to the eye. A classic example is Leonardo da Vinci, who applied these principles while painting the Vitruvian Man. This famous drawing captures the essence of harmony and proportion, which are central to the aesthetics derived from the Fibonacci sequence. Architecture, too, has been deeply inspired by this sequence. The Parthenon in Athens is a prime illustration. Its dimensions allegedly reflect the golden ratio, a concept closely related to the Fibonacci numbers. This ratio, approximately 1.618, creates a sense of balance and beauty that has captivated people for centuries. Architects have used these principles to guide design choices, ensuring that their buildings resonate with a natural sense of proportion. Another captivating instance can be observed in modern design, particularly in digital media and graphic arts. The Fibonacci sequence serves as a guideline for achieving visual harmony. Tech designers and artists often employ this series when creating layouts, enhancing user experience by directing viewers' attention through a rhythmic flow of information. This not only makes for aesthetically pleasing content, but also improves functionality. Even in music, Fibonacci numbers find their way into composition. The structure of certain songs or pieces often coincides with these numbers, either through the arrangement of notes or the overall timing of phrases. The Italian composer Ottorino Respighi utilized the Fibonacci sequence in some of his works as a means to create rhythms that captivate the listener's ear. Noticeable occurrences of this sequence extend to biology as well. The branching of trees is a perfect example where each new branch bifurcates in a manner consistent with Fibonacci numbers. This allows trees to optimize space and sunlight capture as they grow upwards. Similarly, the arrangement of leaves around a stem is designed to maximize exposure to sunlight while minimizing shadowing between them, an elegant aspect of life that reflects these mathematical principles. In the world of finance, traders and analysts use the Fibonacci sequence to inform their strategies. For instance, Fibonacci retracement levels help identify potential reversal points in market trends. Investors often rely on this mathematical model to optimize their buying and selling strategies, making it a valuable tool in the chaotic world of stock trading. The mesmerizing characteristics of the Fibonacci sequence extend into the realm of human emotions as well. Many psychological studies suggest that people demonstrate a penchant for patterns in nature and design that echo Fibonacci principles. The allure of symmetry and proportion resonates deeply with our sense of aesthetics, making us subconsciously drawn to these patterns in our environment. The Fibonacci sequence serves as a reminder of the intricate link between mathematics and the world around us. It invites curiosity and encourages exploration of the systems that govern our universe. This delicate interplay manifests in the spirals of galaxies, the layout of galaxies, and even the microscopic patterns found in crystals. As you explore art, nature, architecture, and design, remember the elegance of the Fibonacci sequence. It demonstrates the beauty that emerges when mathematics intertwines with the world. It is an invitation to observe, appreciate, and find harmony in the world's natural order, which may often seem chaotic, but follows a sublime pattern hidden beneath the surface. So next time you find yourself in a tranquil garden or gazing at a magnificent piece of art, take a moment to reflect on the Fibonacci sequence. Consider how this simple yet profound pattern connects all these remarkable aspects of life, blending mathematics, beauty, and nature into a seamless whole. By understanding this sequence, we gain insight not only into numbers, but also into the very fabric of existence. Every petal, leaf, and architectural delight tells an intricate story of numbers, patterns, and relationships that enrich our experience and inspire awe in the wonders of our world. The golden ratio is a fascinating mathematical concept that has captivated artists, architects, and mathematicians for centuries. It is an irrational number, approximately equal to 1.618, and is often denoted by the Greek letter phi, chi. This unique number appears frequently in nature, classical art, and various forms of geometry, and it is renowned for its aesthetic quality, often regarded as a standard of beauty. Imagine standing in the midst of a lush forest. As you gaze around, you might notice the arrangements of leaves and flowers, the shapes of shells, or even the proportions of a tree trunk. These natural patterns often reveal the golden ratio at play. For instance, when you look closely at a sunflower, you will spot that the number of spirals in one direction compared to the other closely resembles the golden ratio. Similarly, the arrangement of seeds in a pine cone or the spirals of a nautilus shell also reflect this divine proportion, harmonizing form and function in a way that is visually stunning. Turning our attention to classical art, we can find the golden ratio woven into the fabric of many famous masterpieces. The Parthenon, a grand temple in Athens built in the 5th century BC, is often celebrated for its striking beauty, and its dimensions are thought to embody this special ratio. Many art historians believe that the architects utilized this mathematical harmony to create a sense of balance and order that resonates with our understanding of beauty, even centuries later. The golden ratio has also significantly influenced artists such as Leonardo da Vinci. One of his most celebrated works, the painting The Last Supper, is believed to be closely aligned with the golden ratio. The dimensions of the table and the placement of figures within the scene exhibit this captivating ratio, guiding the viewer's eye through the artwork in a pleasing manner. It seems that Da Vinci understood the psychological effects of this ratio and harnessed it to evoke emotions and encourage deeper engagement with his art. Geometry, the study of shapes and their properties, is another domain where the golden ratio shines brightly. In simple terms, if you take a line segment and divide it into two parts, A and B, the ratio of the whole segment to the longer part, A, should be equal to the ratio of the longer part, A, to the shorter part, B, establishing the golden ratio. This relationship is not just a curious feature of numbers. It can be found in the arrangement of a pentagon, the perfect proportions of a rectangle, and even in fractals, like the famous Fibonacci sequence, where each number is the sum of the two preceding numbers, leading to ratios that approach that magical value of 1.618 as you progress further. But why does the golden ratio command such admiration? The answer lies in our innate appreciation for balance and harmony. Studies in psychology suggest that humans are inherently drawn to patterns and ratios that embody symmetry and proportion. The mathematical consistency of the golden ratio resonates deeply with our visual perception, thus inspiring a sense of satisfaction and aesthetic pleasure. Beyond nature and art, the golden ratio can also be traced in modern design and architecture. Contemporary structures often draw upon this ageless principle to create buildings that evoke admiration and enjoyment. For instance, the design of the famous Sydney Opera House incorporates the golden ratio in its sail-like roof. Similarly, tech giants like Apple frequently apply this proportion when creating sleek product designs, ensuring that their gadgets are not only functional, but also visually appealing. Furthermore, the allure of the golden ratio goes beyond physical manifestations. It encourages us to look for harmony and connectivity in our lives. The balance found in the ratio can serve as an analogy for our personal lives, reminding us to seek equilibrium in all aspects, whether it be work and play, family and solitude, or ambition and contentment. In the world of music, the golden ratio also makes an appearance. Composers have long recognized that structures that reflect balance and proportion often lead to harmonious melodies. Certain pieces reveal tempo changes or shifts in dynamics that align with this mathematical ratio, creating a compelling listening experience. From Bach to Beethoven, the presence of the golden ratio adds an intriguing layer of depth to musical compositions. As we journey through our lives, the golden ratio invites us to explore how interconnected our world truly is. From the spiraling galaxies above to the intricate patterns of a snowflake, this irrational number reveals the underlying order of existence. It reminds us that beauty is not merely subjective, but can often be analyzed and understood through the lens of mathematics. The golden ratio transcends cultural boundaries, serving as a universal standard for beauty and proportion. As a number that appears consistently across various disciplines, it serves as a bridge connecting science, art, and nature. Embracing its relevance encourages us to find inspiration in both the ordinary and the extraordinary, revealing the elegance that surrounds us daily. To appreciate the golden ratio fully, one need only to look around. Whether it's examining the elegance of a flower, pondering the architectural marvels of our cities, or reflecting on the balance within ourselves, the golden ratio resonates profoundly with our inherent sense of beauty and order. By allowing this understanding to permeate our thoughts and actions, we can enhance our experiences, inviting a deeper engagement with the world around us. In our quest for meaning and beauty, the golden ratio stands as a timeless symbol of the intricate patterns interwoven into the fabric of existence. So, Next time you find yourself in a space that inspires you, take a moment to reflect. Does this environment echo the harmony of the golden ratio? In exploring this enchanting number, you might uncover an appreciation for the delicate balance that connects us to nature, art, and each other. In the vast tapestry of nature, there exists an intriguing phenomenon known as fractals. These complex, self-similar patterns are a captivating representation of the beauty inherent in mathematics, woven into the very fabric of the natural world. Fractals can be found all around us, from the rugged coastlines that shape our lands to the delicate intricacies of snowflakes and the structured elegance of plants. Let's explore these mesmerizing patterns and discover how they reveal the interplay between math and nature. One of the most familiar examples of fractals can be found along coastlines. The jagged edges of a shoreline, when observed closely, exhibit intricate, repeating patterns. Each curve and indentation reflects a similarity to larger sections of the coast, no matter how far you zoom in. The more you examine a coastline, the more you notice these repeating designs. This property is known as self-similarity, and it reveals a remarkable feature of fractals. They can be infinitely intricate. In essence, a small piece of the coastline reflects the overall form of the larger structure, showcasing how nature often operates in scales both great and small. Another fascinating display of fractals exists in the delicate beauty of snowflakes. Each snowflake that falls from the sky is a unique creation, but they often exhibit fractal characteristics. As water vapor freezes, it forms intricate, crystalline structures. These crystals branch out in patterns that replicate their larger forms in smaller scales. When analyzed, scientists have noted that snowflakes can take on a variety of shapes, from hexagonal patterns to more complex arrangements. The stunning symmetry of snowflakes reveals a natural order, demonstrating how fractals bring elegance and complexity to simple elements of water and temperature. When we turn our attention to the plant kingdom, we encounter another remarkable embodiment of fractals. Take a closer look at a fern, for instance. Its leaves unfold in a stunning spiral, with each small leaflet resembling a miniature version of the whole frond. This phenomenon, known as fractal branching, can also be observed in trees. The way branches extend from the trunk mirrors the structure of the tree as a whole, while each smaller branch resembles its parent, creating a harmonious pattern throughout. Flowers, too, exhibit these self-similar patterns. Consider the arrangement of petals or the spirals present in sunflower heads, where the mathematical beauty of nature unfolds. The beauty of fractals is not limited to just the physical forms we observe, but also extends into the world of sound and music. Fractal patterns can be found in the way music develops, where motifs repeat with variations, creating complex auditory landscapes that entertain and engage the listener. Just as in nature, these patterns resonate with us, drawing our attention and evoking emotions. The interplay of tones and rhythms often follows the same principles observed in the natural patterns around us. In the field of science, fractals are not merely an aesthetic phenomenon. They serve as powerful tools for understanding complex systems. Researchers utilize maps of fractal landscapes to analyze geographical features and make predictions about natural disasters. By studying fractal patterns, scientists can gain insights into phenomena such as climate change, forest growth, and even the distribution of galaxies in the universe. This interconnection between mathematical principles and their application highlights the profound relevance of fractals in understanding the world. Fractals also inspire artists and designers, infusing their work with a sense of natural rhythm and beauty. Artists often draw on fractal geometry to create visually stunning pieces that capture the eye and invoke a deeper appreciation for the patterns that surround us. Whether in paintings, sculptures, or digital art, the use of fractals conveys a sense of order and chaos simultaneously, much like life itself, encouraging viewers to pause and reflect. As we delve deeper into the nature of fractals, we cannot overlook the role they play in the structure of our own experiences. Our bodies, too, exhibit fractal-like patterns. From the branching of our blood vessels to the intricate structure of our lungs, nature's design is reflected in our very being. These self-similar patterns highlight the underlying unity of life, showcasing how intricate mathematics plays a role in the simplest aspects of existence. Understanding fractals stimulates our imagination and ignites our curiosity, prompting us to engage with the world around us in new and meaningful ways. By recognizing these patterns, we can cultivate a deeper appreciation for the environment and the intricate designs that nature has to offer. As we explore the fractals in nature, we start to see the mathematical connections that unite our universe, bringing a sense of wonder and intrigue. In exploring the magnificent realm of fractals in nature, we find an invitation to marvel at the beautiful complexity of life. It encourages us to look closer at our surroundings and to appreciate the patterns that might otherwise go unnoticed. So, the next time you find yourself near a shoreline, in a snowstorm, or walking through the woods, take a moment to observe the fractals that envelop you. Allow yourself to be amazed by the intricate relationships that form our world, revealing the inherent beauty of mathematics in the natural landscape. The Mandelbrot set is one of the most fascinating concepts in mathematics, showcasing the beauty that can emerge from simple rules. Imagine a set of complex numbers that creates breathtaking visuals, each layer revealing new intricacies and patterns as you examine it closer. This captivating phenomenon is central to chaos theory and fractal geometry, two fields of study that have reshaped our understanding of complexity in nature and art. At its core, the Mandelbrot set is defined using a simple mathematical formula. It involves taking a complex number, usually represented as a combination of a real part and an imaginary part, and iterating a specific equation. The equation is usually written as z equals z squared plus c, where z starts at 0 and c represents a complex number that defines a point on the complex plane. The magic happens when we repeatedly apply this formula and see which values escape to infinity and which do not. As you visualize the complex numbers on the two-dimensional plane, you'll see a spectacular boundary emerge. The Mandelbrot set itself is typically colored black, representing those complex numbers that remain bounded and do not escape to infinity. Surrounding this black area, you'll find a tapestry of vibrant colors, illustrating the complex behavior of those numbers that do escape. Each color corresponds to how quickly a particular point escapes, creating an ever-changing spectrum that is simply mesmerizing. But what makes the Mandelbrot set truly remarkable is its infinite complexity. No matter how many times you zoom in on the boundary, you will always discover new features and detail. This property of self-similarity is a hallmark of fractals, where parts of the whole may resemble the entirety itself. As you dive deeper, you may find spirals, intricate formations, and patterns that can be reminiscent of nature, such as coastlines, snowflakes, and even clouds. The more you explore, the more diversity you encounter, each iteration revealing a unique aspect of this mathematical wonder. Artists and scientists alike have been mesmerized by the Mandelbrot set. It is not only a representation of mathematical beauty, but also a bridge between mathematics and the visual arts. Many artists have taken inspiration from its intricate designs, creating stunning artworks that echo the complexities of the Mandelbrot set. Imagine swirling forms that mimic the unity of nature and mathematics, showcasing how two seemingly separate disciplines can converge into a singular expression. The application of the Mandelbrot set goes beyond aesthetics. It serves as an important tool in various scientific fields. Its principles are used to understand processes that appear chaotic, but are governed by underlying mathematical rules. For instance, in physics, the Mandelbrot set's characteristics can help scientists comprehend complex systems ranging from fluid dynamics to weather patterns. Additionally, it has applications in computer graphics, where its properties can generate realistic textures and forms in animations and virtual environments. Moreover, the Mandelbrot set is a marvelous example of how simple equations can lead to profound complexity. It opens the door to discussions about chaos theory, which explores how small changes in initial conditions can lead to vastly different outcomes, a concept that can be seen in weather systems, the stock market, and even ecosystems. Through the lens of the Mandelbrot set, we begin to grasp the delicate balance between order and chaos, demonstrating that what may seem random can often have a hidden structure. Many mathematicians explore the boundaries of the Mandelbrot set, seeking out additional layers and captivating details. This exploration can be likened to an archaeological dig, where each discovery reveals new insights and highlights the richness of a seemingly infinite landscape. Each contour and coloring technique applied to the Mandelbrot set can tell a story, offering a glimpse into how mathematics can not only describe the world, but also inspire creativity. Picture yourself wandering through an endless garden, where vivid blooms represent the varied possibilities of mathematical relationship. As you roam, you find each flower uniquely formed, a testament to the power of mathematical structures lying beneath the surface. The Mandelbrot set is this garden, a boundless source of inspiration and wonder, forever inviting exploration and awe. Furthermore, advancements in computer technology have allowed us to visualize the Mandelbrot set in unprecedented detail. High-resolution graphics and powerful algorithms can produce images that reveal the overwhelmingly intricate detail of the set, showcasing qualities that the naked eye might miss. With each technological breakthrough, the beauty of the Mandelbrot set becomes more accessible, inviting everyone to experience the sublime intersection of math and art. The allure of the Mandelbrot set lies in its blend of simplicity and complexity, beauty and chaos. It serves as a reminder that even the most straightforward equations can produce astonishing results. Whether you approach it from a mathematical, artistic, or scientific perspective, the Mandelbrot set offers endless opportunities for contemplation and discovery. As you consider the magnificence of the Mandelbrot set, reflect on how it symbolizes the interconnectedness of all things. Just as tiny seeds can grow into expansive forests, so too can simple mathematical concepts yield profound insights into the universe. This fleeting glimpse into the world of the Mandelbrot set encourages you to ponder the wonders of mathematics, the art that flourishes within it, and the nature of complexity itself. Take a moment to appreciate the remarkable journey the Mandelbrot set represents. Each iteration adds depth to your understanding, inviting curiosity and instilling a sense of wonder. You are witnessing a celebration of mathematical creativity, expressed through the language of numbers, patterns, and beauty. As you explore this captivating set, remember that every aspect of its unfolding story adds to the intricate tapestry of knowledge that connects us all. Fourier transforms are a fascinating and powerful tool in the realm of mathematics and engineering. They allow us to analyze waveforms and signals in a way that unveils the underlying structure of complex phenomena. Imagine listening to a beautiful symphony. Each musical note you hear is a blend of multiple frequencies that come together to create harmony. Fourier transforms provide a way to separate these notes, allowing us to understand each component that contributes to the overall sound. At its core, the Fourier transform takes a time-based signal, like a sound wave, and transforms it into the frequency domain. This transformation reveals the different frequencies that make up your original signal. Think of a painter's palette filled with colors. Each color can represent a different frequency in a sound wave. Just like a painter can mix colors to create beautiful artwork, sound can be composed of various frequencies mixed together, creating complex audio experiences. Understanding the Fourier transform can be likened to deciphering a complicated puzzle. When you look at a puzzle just laid out on a table, it might seem daunting. However, once you begin to categorize the pieces by color or shape, the process becomes more manageable. The Fourier transform does something similar with signals. It isolates the components that often blend together, making it easier to analyze and make sense of the overall signal. Consider a simple sine wave, which represents a pure frequency. It exists solely at one frequency and provides a clear example of how a fundamental frequency looks in the Fourier domain. When you take a square wave, which is more complex and includes a mix of frequencies, Fourier transforms come into play, breaking it down into its fundamental frequencies and harmonics. Each harmonic adds depth and nuance to the sound, illustrating how complex signals can be created from simple sine waves. Applications of the Fourier transform extend far beyond music. In telecommunications, signals must be sent and received clearly and efficiently. Engineers utilize Fourier transforms to analyze the frequencies involved in these signals, ensuring that data is transmitted without loss or distortion. For example, when you make a phone call, your voice is converted into a signal that travels through the air or cables. The Fourier transform helps in managing and maintaining the clarity of that signal throughout its journey. In image processing, the power of Fourier transforms shines as well. When we think of an image, we often consider it to consist of various colors and shapes. However, breaking an image down into its frequency components can reveal important information about its structure. High frequencies may correspond to sharp edges, while lower frequencies often represent smooth, gradual changes in brightness or color. This understanding can lead to advancements in compression algorithms, making it easier to store and transmit images without losing quality. Another interesting application can be found in medical imaging. Techniques like magnetic resonance imaging, or MRE, rely heavily on Fourier transform. They allow medical professionals to visualize the intricate details inside the human body by analyzing the signals produced by atoms in response to a magnetic field. The result is a detailed representation that helps in diagnosing medical conditions and planning treatments. The beauty of Fourier transforms lies in their versatility. They can be applied to different types of data, from audio signals and images to financial data and scientific measurements. This adaptability makes them a valuable tool across a wide range of disciplines. When we consider complex systems, waveforms can often become intricate and difficult to interpret. The Fourier transform helps simplify this complexity by providing a systematic approach to decompose functions into their frequency components. This allows researchers and engineers to identify patterns, analyze behaviors, and make predictions based on their findings. To put this into perspective, have you ever observed a storm brewing? The winds, the lightning, and the rain can all be seen and felt, but understanding the complex interplay of these elements often requires studying weather patterns over time. Similarly, signals can be analyzed, studied, and predictions made about their future states by applying Fourier transforms. In the world of music production, producers and sound engineers rely on the principles of Fourier analysis to create clarity in their tracks. By understanding which frequencies may clash or desire emphasis, they can manipulate sound to craft the desired auditory experience. Equalizers, audio filters, and even effects like reverb are all developed with the knowledge gleaned from Fourier transforms. The concept of Fourier transforms may seem abstract at first, but they represent a crucial step in bridge building between theory and real-world applications. They help us make sense of the world, revealing the hidden structures that comprise seemingly chaotic signals. As we continue to advance technologically, the importance of Fourier transforms will only grow. They are at the heart of numerous innovations, allowing us to delve deeper into previously unchartable territories. Through the lens of frequency analysis, we can unveil new dimensions of understanding, leading to discoveries that enrich our lives and transform industries. In essence, Fourier transforms act like a powerful microscope for waveforms and signals, magnifying their details and intricacies, making the invisible visible. They demystify the complexity of sound, images, and various other data types, offering insights that propel science, technology, and art forward. Whether it's in designing the latest smartphones, improving medical imaging techniques, or creating the next viral song, the Fourier transform remains a crucial ally in exploring our vast, intricate world. Pascal's triangle is a remarkable mathematical structure that showcases an array of numbers arranged in a triangular form. This triangle is not just a simple arrangement. It earns its name from the French mathematician Blaise Pascal, who studied its properties extensively in the 17th century. However, the triangle's roots can be traced back to ancient civilizations in China, Iran, and Italy, making it a truly cross-cultural marvel. Starting from the top, the triangle begins with a single number, which is 1. As you move downwards, each number inside the triangle is derived from the two numbers directly above it. For instance, the second row contains the numbers 1 and 1, and the third row holds the number 2, which is the sum of the two ones above it. This pattern repeats and creates additional rows, generating a beautiful geometric shape that expands infinitely. As we delve deeper into Pascal's triangle, we can uncover distinct patterns that lie hidden beneath the surface. A striking feature is that each row corresponds to the coefficients found in the binomial expansion. The first row represents the expression a kb raised to the power of 0, resulting in 1. The second row corresponds to a kb raised to the power of 1, giving coefficients of 1 and 1. Continuing this way, the third row relates to a gb squared, producing coefficients of 1, 2, and 1. This relationship extends throughout the triangle, illustrating how binomial coefficients grow in size and complexity with each subsequent row. Another fascinating aspect of Pascal's triangle is its connection to combinatorics, particularly when counting combinations. The numbers in each row represent the ways to choose elements from a larger group. For example, the number in the third row of the triangle signifies the number of ways to choose two elements from a set of 3, or simply the combination formula expressed as 3 choose 2. Establishing this connection transforms what may seem a mere arrangement of numbers into a dynamic tool for solving real-world problems involving probabilities and selections. Exploring further, we discover even more intricate relationships within Pascal's triangle. For instance, one of the most visually striking patterns is the appearance of triangular numbers found along the left edge of the triangle. As one moves to the right edge, the numbers represent the successive integers. Additionally, the sum of the numbers in any given row equals 2 raised to the number of that row. For example, the sum of the coefficients in the 5th row is 32, as it corresponds to 2 raised to the power of 5. The triangle is not just home to rational coefficients. It also reveals surprising connections with Fibonacci numbers. If you take the sum of the diagonals of Pascal's triangle, you will rediscover the sequence of Fibonacci numbers. Starting from the edges and moving inward, the sums yield these numbers, illustrating the enchanting interplay between different mathematical concepts. Moreover, when examining Pascal's triangle through the lens of geometry, things become even more brilliant. The arrangement of the numbers can be creatively connected to a variety of geometric shapes, such as hexagons. When connecting every second number in the triangle, we form a hexagonal pattern that illustrates how numbers relate to each other spatially, offering a fresh perspective on mathematical structure. The beauty of Pascal's triangle extends beyond the realm of pure mathematics. It also engages with the world of computer science. Algorithms and programming techniques often rely on the patterns within the triangle to efficiently solve problems related to combinatorial logic and data structures. For instance, dynamic programming leverages the triangle's recursive nature, breaking down complex problems into simpler, more manageable pieces. In the realm of art and creativity, the allure of Pascal's triangle can inspire design, pattern creation, and even musical composition. As individuals recognize the arrangement of numbers and the symmetries that emerge, they can draw on these features to elevate their crafts into new dimensions. Artists and musicians alike can utilize these mathematical principles to enhance their work, creating symmetry or rhythm that resonates harmoniously with their audiences. Finally, let's not overlook the triangle's statistical applications. In probability, the coefficients of the triangle are used to calculate probabilities in binomial distributions. This intersection of mathematics and statistics demonstrates how what may initially appear as a simple triangular construct can play a crucial part in analyzing data and understanding randomness in the universe. As we navigate the layers of Pascal's triangle, we tap into a vibrant tapestry woven from numbers, shapes, and connections. From its origins in ancient cultures to its modern-day applications across various disciplines, Pascal's triangle stands not only as a source of fascination for mathematicians, but also as a bridge to the wonders of the universe. It teaches us to appreciate the harmony present in nature, art, and the logical structure of our world. Through its exploration, we come to see that mathematics is not merely a collection of formulas and numbers. It is a language embodying the patterns and intricacies of existence itself, inviting anyone with curiosity to unpack its infinite tales. Magic squares have fascinated cultures around the world for centuries. These intriguing mathematical constructs exist as square grids filled with distinct integers, arranged in such a way that the sums of the numbers in each row, column, and both main diagonals are equal. This constant sum is known as the magic constant or magic sum. The beauty of magic squares lies not only in their mathematical precision, but also in their cultural significance and historical narratives. One of the earliest known magic squares comes from ancient China. The Luoshu Square, a 3x3 magic square, is steeped in legend and is believed to have been discovered on the back of a turtle emerging from the Yellow River. In this square, the numbers 1 through 9 are arranged so that every row, column, and diagonal adds up to 15. This simple yet profound arrangement has inspired countless scholars and enthusiasts throughout history, illustrating how numbers can unveil hidden beauty in our world. Moving across the globe, in the Islamic Golden Age, scholars like al-Buni explored the mysticism of numbers through magic squares. They not only studied their mathematical properties, but also delved into their spiritual symbolism. It was believed that these squares held the power to bring harmony and balance to one's life. Al-Buni created extensive collections of squares, sometimes with elaborate geometric designs, incorporating various mathematical principles, which were often linked to astrological beliefs, enhancing their mystery and allure. In Europe, during the Renaissance, magic squares caught the attention of mathematicians and artists alike. The most famous example is the 4x4 magic square, found in Albrecht Dürer's engraving titled Melancholia Ein. In this artwork, the numbers in the square total 34, illustrating the magic constant of a 4x4 square. The inclusion of such an intricate design hints at the Renaissance's obsession with incorporating mathematics into art, revealing the underlying order of the universe through creativity. Dürer's magic square not only captivated mathematicians, but also served as an emblematic representation of the harmonious relationship between art and science. As we delve deeper, consider the application of magic squares in games and puzzles. For example, Sudoku can be seen as a dynamic and modern derivative of magic square. While traditional magic squares require every row, column, and diagonal to equal the same magic constant, Sudoku adds layers of complexity and rules that challenge the mind. Nevertheless, the roots of magic squares can still be traced back to these ancient grids, showcasing how mathematical principles endure and evolve through time and culture. Moreover, there exist larger magic squares, including those of order greater than 4. These squares can be quite complex, yet their fundamental properties remain. For example, the 5x5 magic square ensures that each row, column, and diagonal sums to 65 Dauer. Engaging with these larger squares often leads to various methods for their construction, drawing upon techniques that involve arithmetic sequences, patterns, and even computer algorithms today. Interestingly, magic squares have made their way into various cultural traditions. In some cultures, they are utilized in talismans, believed to evoke protection or success. For instance, the Janus square, a 3x3 magic square used in mystic practices, reflects a blend of art, religion, and numerology, revealing how mathematics interconnects with human experience. Exploring the role of magic squares in different cultures, we find that they often transcend mere numbers. In South America, indigenous peoples crafted magic squares that communicated sacred beliefs and celestial observations, linking their cosmology with earthly existence. This reflects the universal truth that humans have always sought to understand the world around them through patterns and symbols. One can also appreciate the artistic representations of magic squares. Artists from various cultures have depicted these squares in mosaics and carvings, illustrating how these numerical puzzles translate into visual language. The interplay of mathematics and art creates an appealing narrative that resonates across cultures, transcending language and time. Even in modern times, the allure of magic squares continues. Mathematicians and enthusiasts engage in solving complex challenges and creating new variations. With advancements in technology, computer algorithms are now being employed to generate and analyze magic squares, leading to new discoveries and insights into this ancient subject. To fully appreciate the significance of magic squares, consider their connections to broader mathematical concepts. The study of magic squares relates to combinatorial design, group theory, and even number theory. The intricate balance found in a magic square highlights the elegant interplay between mathematics and logic, encouraging a deeper appreciation for the patterns that govern our world. Ultimately, magic squares are more than mere mathematical curiosities. They serve as windows into human creativity, intellect, and cultural expression. The ability to arrange numbers in such a captivating manner unites us across time and space, inviting us to ponder the mysteries and relationships that intertwine mathematics with human experience. As you contemplate the fascinating realm of magic squares, remember the countless individuals across history who have marveled at their intrigue. From ancient Chinese legends to Renaissance masterpieces and modern explorations of mathematical theory, magic squares remind us of the beauty found within numbers and the shared curiosity that drives humanity to seek understanding, connection, and harmony in a world that often seems chaotic. The Collatz Conjecture is a fascinating mathematical puzzle that has intrigued both amateur enthusiasts and seasoned mathematicians for decades. At first glance, the conjecture appears deceptively simple, but beneath its straightforward exterior lies a depth that continues to elude proof. The process begins with any positive integer. You start with this number and apply a simple set of rules. If the number is even, you divide it by 2. If it's odd, you triple it and then add 1. This process creates a sequence of numbers derived from the original. The question at the heart of the Collatz conjecture is straightforward yet profound. No matter which positive integer you start with, will that sequence eventually lead to the number 1? Let's illustrate this with an example. Imagine we begin with the number 6. Since 6 is even, we divide it by 2, which gives us 3. Now we have an odd number, so we apply the next rule. We triple 3, obtaining 9, and then add 1 to get 10. 10 is even, so we divide by 2 to get 5. 5 is odd, so we triple it and add 1 to get 16. Continuing this process, we eventually arrive at 1. Each number in this sequence naturally flows to the next, creating a trail through seemingly random territory that always culminates at 1. For another instance, consider starting with the number 7. Following the rules, 7 is odd, so we triple it and add 1, resulting in 22. 22, being even, is halved to 11. 11, once again odd, leads to 34. This sequence continues, but strangely enough, regardless of the twists and turns, it will also ultimately lead to 1. However, this is where the mystery lies. While numerous positive integers have been tested, showing that they do converge to 1, there's no formal proof that ensures all positive integers will behave the same way. The lack of a comprehensive solution adds a compelling layer to the conjecture. It serves as a reminder of the unpredictable nature of numbers, inviting both theoretical exploration and practical experimentation. Many mathematicians have taken up the challenge of proving or disproving the conjecture. Some have looked at larger sequences and higher ranges of numbers, while others have approached it through statistical analysis. Each has its methods and perspectives, creating a rich tapestry of ideas surrounding this single mathematical inquiry. The Collatz conjecture also serves as an insightful lesson about simplicity in complexity. Though the rules are easily understandable, the outcomes are anything but straightforward. One cannot help but marvel at how such a simple set of rules could lead to such a challenging and unsolved problem. It echoes through the fields of mathematics, reminding us that curiosity and exploration can still pave the way to new insights, regardless of how trivial they may initially seem. Many get drawn into the allure of the Collatz Conjecture as they contemplate the different paths numbers take. This philosophical question touches upon the nature of infinity and the endless possibilities that lie within the realm of integers. The process also stimulates an urge for deeper investigation, inviting thinkers to search for patterns among various sequences. For those passionate about mathematics, the opportunities for exploration are abundant. By plotting different starting numbers and observing their sequences, one can quite literally visualize the Collatz journey. Each graph, each path, serves as a unique fingerprint of the number's behavior. As you delve deeper into the patterns, you might find peculiarities and emergent behaviors that delight the mind. Another interesting aspect is how some numbers seem to take longer to reach one compared to others. For instance, the number 27 has a particularly long sequence, taking an astonishing 111 steps before arriving at 1. The complexity of this journey further amplifies curiosity and fuels ongoing discussions among those captivated by this mathematical inquiry. Ultimately, the Collatz Conjecture is more than just a mathematical problem. It is a gateway into the mysteries of mathematics as a whole. It highlights the joy of discovery that comes from asking questions and exploring possibilities. It speaks to the very essence of scientific inquiry, where simple assumptions can lead to intricate and profound insights. To engage with this conjecture is to embrace a journey of thought where certainty is elusive, yet curiosity flourishes. Every step taken along the path to understanding only deepens the appreciation for the marvelous world of mathematics. As new generations of thinkers, dreamers, and explorers engage with this simple yet tantalizing question, the quest for knowledge continues, igniting the spirit of curiosity that has driven humanity's pursuit of understanding since the dawn of time. In the landscape of mathematics, the Collatz Conjecture stands as a testament to both human ingenuity and the boundless complexities that numbers can embody. It serves as a gentle reminder that sometimes the most profound mysteries are found within the simplest of concepts, inviting us to explore, ponder, and dream. Prime numbers have fascinated mathematicians for centuries. These numbers, defined as those greater than 1 that have no positive divisors other than 1 and themselves, form a unique and essential part of the mathematical landscape. Imagine the prime numbers as special gems scattered throughout the vast field of integers. They shine brightly, sometimes appearing in clusters, but often seem to vanish mysteriously into the distance. The journey into the world of prime numbers begins with the smallest on the number line: 2, 3, 5, 7, 11, and so on. Each prime is an individual, standing alone, not divisible by any other number except for 1 and itself. This exclusivity renders them unique. But what makes them so special? Beyond their definition lies a plethora of intriguing characteristics and patterns that often leave scholars puzzled. One of the most captivating aspects of prime numbers is their unpredictable distribution. Despite there being an infinite number of primes, they do not appear at regular intervals. For instance, the difference between consecutive primes can vary significantly. The gap between the first primes, such as 2 and 3, is merely 1, but as you climb higher on the number line, these gaps can widen dramatically. There is no clear formula that dictates where the next prime will fall, or how far away it might be. This makes the pursuit of primes akin to a treasure hunt. Sometimes you strike gold, while at other times there seems to be nothing for miles. As the number line extends, mathematicians have made numerous attempts to understand the distribution of primes. One notable result is the prime number theorem, which provides a way to estimate the number of primes less than a given number. It suggests that the distribution of prime numbers becomes sparser as numbers grow larger, but they still appear with a sort of regularity. This theorem can be visualized as a spiderweb stretching infinitely outward, where the strands represent clusters of primes, always moving farther apart. What's more intriguing is the existence of something known as twin prime. These are pairs of prime numbers that have a difference of 2. An example is the pair of 5 and 7. Such pairs are rare, but their existence raises questions about whether there are infinitely many twin primes. Despite considerable effort, this remains an unsolved problem, an enticing mystery woven into the fabric of mathematics. Another fascinating phenomenon is the Collatz Conjecture, which posits that every even integer greater than 2 can be expressed as the sum of 2 prime numbers. This conjecture has been tested extensively and holds true for very large numbers, yet a formal proof has yet to be established. The idea of unlocking yet another secret of primes tantalizes those who strive to unravel mathematical enigmas. As we delve deeper into prime numbers, we encounter concepts like Mersenne primes, which take the form of 2 to the power of p-1, where p is a prime number. These primes have drawn attention not only for their rarity, but also for their connection to perfect numbers, another elusive category in mathematics. Perfect numbers are those whose divisors sum to the number itself. Exploring the links between Mersenne primes and perfect numbers can lead one down an intriguing path filled with unexpected connections and relationships. The digital age has breathed new life into the search for prime numbers. Computers and advanced algorithms have enabled mathematicians to discover ever larger primes, breaking records once thought unachievable. These colossal primes are not merely curiosities. They play a crucial role in modern cryptography. Many encryption methods rely on the difficulty of factoring large numbers into their prime components, allowing for secure communication in an increasingly interconnected world. Yet, even with all the advances in technology and theory, prime numbers retain an air of mystery. The Riemann Hypothesis, one of the most famous unsolved problems in mathematics, seeks to understand the distribution of primes by exploring the zeros of the Riemann zeta function. This intricate relationship hints at a deeper underlying order governing the primes, an elusive truth mathematicians have pursued for over a century. In addition to all their mathematical significance, primes are also a source of inspiration in art, music, and literature. They appear not only in equations, but also in poetic rhythms, musical compositions, and even in the structures of famous architectural marvels. The elegance and simplicity of prime numbers captivate the human imagination, inviting exploration and creativity in unexpected ways. Prime numbers are more than just mathematical entities. They represent a journey into the heart of mathematics, a plane where order meets chaos, where certainty flirts with the unknown. Every discovery, every pattern recognized, only serves to deepen the intrigue surrounding these numbers. As we journey through the unfolding mysteries of primes, we find that they are not merely a subject of study, but a bridge connecting mathematics, nature, and human intellect. In conclusion, prime numbers stand as timeless sentinels in the world of mathematics. They invite us to question to explore and to search for deeper meanings hidden within the fabric of numbers. Each prime is a piece of the puzzle of the universe, a testament to the beauty and complexity of mathematics, and an endless source of inspiration for those daring enough to embark on the quest to understand them. Let the mystery of prime numbers continue to spark curiosity and wonder in every generation, illuminating paths that lead to new discoveries and insights. The Riemann hypothesis is one of the most famous and long-standing unsolved problems in mathematics. It revolves around the Riemann zeta function, a complex function that encodes fascinating properties of numbers, particularly primes. At its core, this hypothesis proposes a deep connection between the distribution of prime numbers and the zeros of this function. To understand the Riemann hypothesis, we first need to delve into what prime numbers are. Primes are the building blocks of all integers, numbers greater than 1 that have no positive divisors other than 1 and themselves. For example, the numbers 2, 3, 5, 7, 11, and 13 are all prime. They play a vital role in number theory, much like atoms do in chemistry. Yet, what is intriguing about primes is how they appear in the vast ocean of numbers. They seem scattered, with no apparent pattern, but this is where the Riemann zeta function comes into play. The Riemann zeta function is typically denoted as S, where S is a complex number. It can be expressed as an infinite series when the real part of S is greater than 1, and it converges to a value that contains rich information about prime. When mathematicians look at the zeros of the Riemann zeta function, those specific values of S for which S equals 0, they find a profound link to the distribution of prime numbers. The Riemann hypothesis states that all non-trivial zeros of the zeta function lie on a specific line in the complex plane, known as the critical line, where the real part of S is equal to 1/2. This conjecture, proposed by Bernhard Riemann in 1859, suggests that every zero can be represented as 1/2 plus some imaginary component. This singular assertion has captivated mathematicians for over 160 years. Exploring the implications of this hypothesis reveals enchanting possibilities. If proven true, it would provide insights into how primes are distributed among the integers, offering a clearer understanding of their elusive nature. For instance, one of the results influenced by the hypothesis is the prime number theorem, which describes how the prime numbers become less frequent as numbers grow larger, yet they never completely vanish. As mathematicians grapple with the Riemann hypothesis, they have unearthed various results that suggest the hypothesis might indeed hold. They have computed billions of zeros of the Riemann zeta function, and every one of them has been found to lie on the critical line. However, a general proof that applies to all such zeros remains elusive. Delving into the history of the Riemann hypothesis unveils a cast of characters who have contributed to its legacy. Figures like David Hilbert, who placed it at the center of his now famous list of 23 unsolved problems in mathematics, presented in 1900, and John von Neumann, who believed that progress on the hypothesis could lead to advancements across many areas of mathematics and science. It's also interesting to note that the Riemann hypothesis is connected to various fields beyond pure mathematics. In physics, it has applications in quantum mechanics and statistical mechanics, where the zeros of the zeta function find analogs in energy levels of complex quantum systems. Moreover, it has links to cryptography and computer science, particularly since prime numbers are fundamental to modern encryption methods. Efforts to prove or disprove the Riemann hypothesis have led to the development of new areas of mathematics, like analytic number theory, which combines analysis and number theory to study the properties of integers more deeply. Researchers have developed extensive computational tools to explore the zeta function and investigate the distribution of its zeros, revealing unexpected patterns and symmetry. Despite the profound implications of the Riemann hypothesis, much about it remains enigmatic. Some mathematicians view it as a cornerstone of the mathematical universe, representing the intersection of numerical patterns and complex analysis. Others find it a challenge that invites exploration and inquiry. As they continue to study it, new techniques, new insights, and new connections to other mathematical concepts often emerge. In the broader landscape of mathematics, the Riemann hypothesis stands as a towering figure, representing the beauty and complexity of the mathematical realm. It serves as a beacon for aspiring mathematicians and a source of inspiration for those seeking to understand the underlying structures that govern numbers. As discussions about this legendary hypothesis continue, it embodies the spirit of mathematics, curiosity, creativity, and the relentless pursuit of truth. Whether through deep theoretical investigation or computational exploration, the journey toward resolving the Riemann hypothesis is one of excitement and discovery. It reminds us that within the world of numbers lies a treasure trove of mysteries waiting to be unveiled. Each new study, each new computational result, brings mathematicians one step closer to unlocking the secrets of the mathematical universe, with the Riemann zeta function at the heart of this captivating quest. Thus, as we ponder the wonders of the Riemann hypothesis and its implications for our understanding of prime numbers, we are reminded of the beauty of mathematics itself. In its intricate patterns and profound questions, we find infinite possibilities and intellectual adventures that continue to spark our imagination and drive our quest for knowledge. The allure of this legendary hypothesis will undoubtedly endure, making its way through the hearts and minds of mathematicians for many generations to come. Euler's identity, often hailed as one of the most beautiful equations in mathematics, elegantly connects 5 fundamental constants in a harmonious relationship. The formula is expressed as e to the power of pi times I plus 1 equals 0. At first glance, it may seem like a collection of symbols, but when we delve deeper, we uncover the profound connections and insights it offers. To begin understanding Euler's identity, we must first examine the constants it encompasses. The first constant, e, approximately equal to 2.71828, is the base of natural logarithms and is pivotal in calculus, particularly in the context of exponential growth and decay. This number frequently appears in various fields, from finance to biology, embodying the concept of continuous growth. Next, we encounter the imaginary unit, I, which is defined as the square root of -1. While this may seem abstract, imaginary numbers play a crucial role in complex analysis, engineering, and even physics. They allow for solutions to equations that would otherwise be unsolvable within the realm of real numbers, opening doors to new dimensions of understanding. Then we have p, approximately 34159, a transcendental number that defines the ratio of a circle's circumference to its diameter. Its prevalence in mathematics and nature cannot be understated. From geometry to trigonometry, p appears in numerous formulas and describes phenomena ranging from the orbits of planets to the waves of sound and light. The number 1, universally recognized and foundational to mathematics, represents unity and identity. It is the first natural number and serves as a building block for all other numbers. Lastly, we have 0, a symbol for nothingness, yet it signifies an essential concept in mathematics representing balance, and the idea of an absence of quantity. Without zero, our numerical system would be incomplete. When we combine these constants, we see a profound relationship. Euler's identity demonstrates the deep interplay between different branches of mathematics, illustrating how seemingly disparate concepts can converge to form a singular cohesive truth. It illustrates the power and beauty of mathematical thought, where a simple equation can capture the essence of complex ideas. To appreciate this identity further, let us consider its components in a graphical context. The complex plane is a two-dimensional space where the x-axis represents real numbers and the y-axis represents imaginary numbers. When we plot the number e raised to the power of pi times I, we find that it lies on the unit circle, precisely at the point corresponding to 1 on the x-axis. This geometric representation reveals the profound beauty of mathematics, where numbers dance in perfect synchrony, forming shapes and patterns that resonate throughout various disciplines. Moreover, the exponential function, which forms the crux of Euler's identity, exhibits remarkable properties. It is continuous and differentiable, meaning it flows without interruption and has a consistent rate of change. This quality allows mathematicians and scientists to model a myriad of natural phenomena, such as population growth, radioactive decay, and even the behavior of financial markets. Euler's identity is not merely an equation, but a gateway to exploring further mathematical concepts. Exploring how E and pi relate through the lens of complex analysis uncovers the fascinating world of Fourier Transforms, which have applications in signal processing, image compression, and quantum mechanics. These concepts reach into the depths of modern technology, shaping how we communicate and interact with the world. In a broader sense, Euler's identity invites us to reflect on the nature of mathematical beauty itself. It challenges us to seek connections between concepts that may seem unrelated at first glance. Just as art communicates emotions and ideas through various mediums, mathematics conveys profound truths about reality, revealing underlying patterns and relationships. This constant interaction between beauty and logic is what makes mathematics an art form of its own. The ability to appreciate an equation like Euler's identity requires a shift in perspective, recognizing that what lies beneath the surface is a rich tapestry of ideas, creativity, and human thought. Further, the legacy of Euler's work extends beyond this single equation. His contributions to diverse fields, such as topology, graph theory, and calculus, have laid the groundwork for many mathematical advancements yet to come. It opens doors for us to explore further, to question, and to innovate. In our modern world, where mathematical literacy is increasingly important, understanding the elegance of Euler's identity invites us to appreciate the universal language of mathematics. It prompts questions about the nature of reality, uncovering the myriad ways in which mathematics describes the universe. As we reflect on Euler's identity, we find a connection, a unity that transcends cultures and disciplines. The beauty of this equation resonates not only within mathematical circles, but throughout the creative arts, science, and everyday life. In conclusion, Euler's identity stands as a testament to the beauty and interconnectedness of mathematics. It serves as a reminder of the elegance that dwells within the world around us, encouraging us to seek out the relationships in our lives, be they numerical, artistic, or philosophical. Whether we explore these connections in numbers, nature, or even music, the journey of understanding is one of wonder and creativity, illustrating that at the heart of complexity often lies simplicity and beauty. The Möbius strip is an intriguing and captivating object, in the realm of mathematics and geometry. It's a structure that has fascinated thinkers for centuries, offering a stunning visual and spatial twist that defies our everyday understanding of surfaces and dimensions. To fully appreciate the wonders of the Möbius strip, let's delve into its unique properties and the concepts that make it so remarkable. Imagine taking a rectangular strip of paper. The first step in creating a Möbius strip is twisting one end of the strip by 180 degrees. Next, you would join this twisted end to the other end, forming a loop. At first glance, it may seem like a simple loop of paper, but herein lies the magic. Unlike a conventional ring, a Möbius strip has only one continuous side and one continuous edge. This means that if you were to draw a line down the center of the strip and keep moving along it, you would eventually return to your starting point, having covered both sides of the strip without lifting your pencil. The properties of the Möbius strip extend far beyond its captivating shape. It serves as a fascinating entry point into the mathematical field known as topology, which focuses on the properties of space that are preserved under continuous transformations. In topology, the Möbius strip is often cited as a classic example of a non-orientable surface. This implies that if you were to walk along the surface of the strip and return to your starting point, you would find yourself upside down. Such a property challenges our intuitive perception of geometry and the dimensions around us. The Möbius strip is not just a theoretical concept. It has practical applications too. For instance, it can be found in various fields, such as art, architecture, and engineering. Artists like M.C. Escher have used the Möbius strip in their work to illustrate concepts of infinity and paradox. These visual representations often challenge the viewer's perception, allowing for an exploration of depth and dimension that transcends traditional two-dimensional art. In the engineering world, the Möbius strip's unique structure has inspired designs in conveyor belts and roller coasters. A Möbius belt can run continuously without needing to be turned over for maintenance, which allows for more efficient use of resources. This intriguing application demonstrates how a mathematical concept can influence practical solutions in the physical world. Moreover, the Möbius strip has connections to concepts far beyond geometry, reaching into the realms of physics and philosophy. In the realm of physics, the notion of a non-orientable surface prompts unique considerations in areas such as string theory and quantum mechanics, where the nature of dimensions and the universe is endlessly explored. Philosophers, too, have drawn on the Möbius strip as a metaphor for ideas that revolve around unity and duality, often prompting discussions about the nature, existence, and perception. One delightful way to visualize the Möbius strip in action is through the use of scissors. If you take a standard Möbius strip and cut it along its center line, instead of producing two separate strips, you'll end up with one larger strip that has two twists in it. This surprising outcome exposes the playful nature of mathematics, where our expectations can be turned upside down, just like the surface of the Möbius strip itself. If you want to dive even deeper into its features, consider the relationship between the Möbius strip and Klein bottles. Much like the Möbius strip, a Klein bottle is a non-orientable surface, but it has a more complex structure that cannot be fully represented in three-dimensional space. While you can create a Möbius strip with just a strip of paper, a Klein bottle requires a fourth dimension to be fully realized. This makes the exploration of these spaces deeply fascinating, as it stretches our imagination beyond the conventional constraints of our three-dimensional world. Engaging with the Möbius strip can also inspire creativity. It encourages thinking outside the box and embracing the complexities of different perspectives. In art and design, the principles illustrated by the Möbius strip can lead to innovative practices that reflect continuity and transformation, concepts that resonate deeply in both creative and logical processes. In summary, the Möbius strip is much more than simply a mathematical curiosity. It embodies a wealth of knowledge that bridges multiple disciplines, from geometry and topology to art and philosophy. As we explore these intricate surfaces, we uncover a deeper understanding of the complexities of space and existence. The Möbius strip encourages us to reflect on how we perceive the world around us, inviting us to perceive the connections and paradoxes that lie just beneath the surface. Whether through its applications in design or its philosophical implications, the Möbius strip remains a profound symbol of unity and complexity, forever captivating our minds and imagination. Hexagonal honeycombs are a remarkable feature of nature, showcasing the incredible skills of bees and the mathematical principles that govern space and efficiency. These beautiful structures, forged from simple hexagonal shapes, stand as a testament to both the ingenuity of bee behavior and the fascinating world of geometry. At first glance, a honeycomb looks like a simple grid of wax cells. However, when you dive deeper into its design, you'll discover that it is not just efficient, but also strong. Each hexagon in a honeycomb has been carefully crafted by bees to maximize space and resources. This design allows bees to store honey and pollen while also providing a nursery for their young. The hexagonal shape optimally uses the least amount of wax to create the largest possible volume within the minimum wall length. It's interesting to note that bees don't just stumble upon this shape, they instinctively know how to build it. This instinctual behavior has fascinated scientists and mathematicians alike. The hexagonal structure has been studied extensively, revealing that this form is mathematically proven to be the most efficient way to partition a plane. Unlike squares, which leave unused corners, or triangular shapes, which do not allow for maximum volume, hexagons fit together perfectly without leaving gaps. Imagine trying to pack different shapes into a box. When you use squares, there are always small spaces left unfilled. Triangles might fit in a different way, but they also leave gaps. In contrast, hexagons tessellate seamlessly, meaning they can completely fill a space without any wasted area. This is why hexagonal grids are found in various natural arrangements beyond beehives, like in the formation of snowflakes or the patterns of certain minerals. The efficiency of the honeycomb has far-reaching implications outside of nature as well. Engineers and architects have taken cues from this structure to create efficient, lightweight designs in various fields. For example, you might see hexagonal patterns in modern architecture or in the design of transportation layers, where weight savings can lead to greater fuel efficiency. This natural marvel also plays a vital role in the environment. The hexagonal structure of honeycombs not only supports the life cycle of bees, but also contributes to pollination, which is essential for the growth of many foods and flowers. By providing a safe and efficient space for bees, these honeycombs help maintain a delicate balance in ecosystems. Furthermore, the production of beeswax, from which honeycombs are made, is an outstanding example of cooperation. Each bee in the colony has its own role, and they work tirelessly as a collective unit. The process begins when worker bees collect nectar from flowering plants. Back at the hive, they transform this nectar into honey, which then requires proper storage in these meticulously constructed cells. The bees work together to form the hexagonal cells, which offer durability while using the least amount of material possible. In considering the architectural beauty of these structures, one cannot overlook their thermal properties. Hexagonal patterns provide excellent insulation for the hive. The combination of design and structure creates a microclimate that helps maintain a consistent temperature, protecting the precious honey and larvae within the hive. This specialized architectural knowledge, passed down through generations, allows bees to thrive even in varying climatic conditions. The allure of honeycomb doesn't end with its geometry or the preparation it offers. The glaze of golden honey held within these cells has captured human interest for centuries. Facades of crystal-clear honey glistening in the light are not just beautiful. They are a true embodiment of the hard work and precision that goes into each honeycomb structure. If you have ever tasted honey, you might have noticed the distinct flavors that differ according to the flowers from which the nectar is harvested. This relationship between bees, plants, and the hexagonal structures built to store their bounty reflects a unique system that emphasizes harmony in nature. Different regions yield different honey, which in turn is a reflection of the diverse ecosystem around them. Honey from clover blossoms tastes distinctly different from that made from lavender or eucalyptus, each with its own unique properties and uses. Additionally, the hexagonal shapes that bees construct can inspire future technologies. Researchers are studying how these natural designs can revolutionize materials science, particularly in creating lightweight yet strong materials for various applications, ranging from construction to aviation. The artistry of honeycomb structures can lead to innovations across different sectors, attesting to the idea that nature often holds the keys to solving human challenges. In summary, hexagonal honeycombs stand as a brilliant example of nature's design efficiency. They remind us of the interconnectedness of life, the importance of cooperation, and the elegance that exists in even the smallest details of our environment. From the way bees utilize their instincts and skills to engineer these intricate structures, to the broader implications of these designs in science and nature, the study of honeycombs offers endless fascination. The balance between efficiency and beauty is perfectly encapsulated in the humble honeycomb, inspiring awe and curiosity about the natural world around us. The Pythagorean Theorem is a fundamental principle in mathematics, particularly in the field of geometry. Often associated with the ancient Greek mathematician Pythagoras, this theorem provides a relationship between the sides of a right triangle, which is a triangle that has one angle measuring exactly 90 degrees. At its core, the Pythagorean theorem can be expressed with a simple equation: a squared plus b squared equals c squared. In this equation, a and b represent the lengths of the two legs of the triangle, while c represents the length of the hypotenuse. The hypotenuse is the longest side of the triangle, opposite the right angle. To better understand this principle, imagine a right triangle where one leg measures 3 units long and the other leg measures 4 units long. If we apply the Pythagorean theorem, we can find the length of the hypotenuse. First, we square the lengths of both legs. 3 squared gives us 9 and 4 squared gives us 16. Then, we add these two results together. 9 plus 16 equals 25. Finally, to find the length of the hypotenuse, we take the square root of 25, which gives us 5. So, in this right triangle, the hypotenuse measures 5 units. The beauty of the Pythagorean theorem lies not only in its elegant simplicity, but also in its wide array of practical applications. This theorem can be utilized in various fields, including architecture, physics, engineering, and even computer graphics. For example, in construction, carpenters rely on this theorem to ensure that structures are built squarely and accurately. By verifying that the lengths of the sides comply with the Pythagorean theorem, they can ensure stability and precision. In physics, the theorem can be employed to analyze vector components. Vectors are quantities that have both magnitude and direction, and often they need to be broken down into their horizontal and vertical components. The Pythagorean theorem allows physicists to calculate the resultant vector, which combines these two components effectively. Additionally, in the world of computer graphics, this theorem serves as a foundational principle for rendering images and animations. When creating realistic graphics, understanding distances and relationships between points in a virtual environment is crucial. The Pythagorean theorem provides a method to calculate the distances between pixels and shapes, ensuring that the visual output is coherent and accurate. Beyond practical applications, the Pythagorean theorem also opens up avenues for exploring deeper mathematical concepts. For instance, it serves as a stepping stone to study more complex topics such as trigonometry, which deals with the relationships between the angles and sides of triangles. Furthermore, the theorem can lead to discussions about the various types of triangles, allowing for the exploration of other formulas and relationships in geometry. Interestingly, the Pythagorean theorem is not limited to right triangles alone. In fact, it has inspired numerous other theorems and principles involving triangles of various types. The relationships established through the Pythagorean theorem can be extended to create new insights and formulas in mathematics. One fascinating aspect of the Pythagorean theorem is the existence of Pythagorean triples. These are sets of three integers that satisfy the condition outlined by the theorem. The most well-known example is the set of numbers 3, 4, and 5. However, there are infinitely many such triples, such as 5, 12, and 13. Exploring these triples reveals an intriguing world of relationships and patterns in number theory. Moreover, the theorem has historical significance, extending far beyond Pythagoras himself. Many ancient civilizations, including the Egyptians and Babylonians, had concepts akin to the Pythagorean theorem. For instance, the Egyptians used a method involving ropes knotted at specific intervals to create right angles, thus applying principles reminiscent of the theorem long before Pythagoras was born. The theorem has evolved over time, with countless proofs developed since its initial formulation. Some of these proofs are geometric, while others use algebraic methods, calculus, or even trigonometric identities. This diversity of proofs highlights the theorem's significance and its robustness as a mathematical truth. In summary, the Pythagorean theorem is a pivotal principle that elegantly connects the sides of right triangles through a straightforward equation: a squared plus b squared equals c squared. Its implications stretch far beyond geometry, playing crucial roles in various fields, such as construction, physics, computer graphics, and number theory. By understanding this theorem, one gains insights into the nature of triangles, distances, and the relationships that govern them. The legacy of the Pythagorean theorem also underscores the interconnectedness of mathematical concepts, revealing the beauty and depth that lies within the realm of mathematics. This theorem continues to be a cornerstone of learning for students and a source of inspiration for mathematicians around the world. Engaging with the Pythagorean theorem opens up a world of exploration, discovery, and endless possibilities in the captivating universe of mathematics. Whether you are navigating the intricacies of numbers, delving into geometry, or just contemplating the elegance of shapes and angles, the Pythagorean theorem remains a guiding light, illuminating the path toward understanding the profound relationships that shape our mathematical landscape. Embracing this theorem leads to not only practical applications, but also a deeper appreciation for the beauty of mathematics. As you reflect on the significance of the Pythagorean Theorem, consider how such a simple equation can yield a wealth of knowledge and inspiration, encouraging further inquiry into the marvelous world of numbers and shape. Once upon a time in the world of game shows, there was a particular challenge that puzzled many contestants, known as the Monty Hall problem. This intriguing scenario takes its name from Monty Hall, the original host of the popular television game show. Let's make a deal. Picture this. You are standing in front of 3 doors. Behind one of these doors is a shiny new car, while behind the other 2 are goats. Yes, goats. The goal is to choose the door with the car behind it. At the start of the game, you choose one door. Let's say you pick door A. At this point, you might feel a mix of excitement and uncertainty. The host, Monty Hall, who knows exactly what lies behind each door, will then open one of the remaining doors to reveal a goat. For example, he might open door B, revealing the unfortunate goat that awaits behind it. Now comes the crucial moment. Monty offers you a chance to switch your choice to door C, or stick with your original choice, door A. It seems only logical to think that it does not matter whether you switch or not. After all, there are 2 doors left, and one of them is sure to have the car. Thus, it feels like you have a 50-50 chance of winning if you decide to switch. However, the surprising truth is that you actually have a better chance of winning the car if you switch. Let us explore how this counterintuitive conclusion comes about, and you will see why so many people find this puzzle fascinating. At the outset, when you choose door A, your probability of picking the car is 1 in 3, or approximately 33%, and the probability that the car is behind one of the other doors, doors B or C, is 2 in 3, or about 67%. This means there is a greater chance that the car is not behind your initially chosen door. When Monty reveals a goat behind door B, this significant piece of information influences your options. Now let us analyze the potential outcomes if you decide to switch. There are 2 situations to consider. The first situation is simple. You initially chose the door with the car behind it, which has a probability of 1 in 3. If you switch in this case, you will lose. On the other hand, if your initial choice was one of the doors with a goat behind it, which occurs with a probability of 2 in 3, switching will lead you to win the car. Thus, by switching, you will win whenever your first choice was wrong, which is the more likely scenario. To make this clearer, let's consider a practical example. Imagine you have 3 doors again, A, B, and C. You choose door A. The possibilities are as follows. 1. The car is behind door A. Monty opens either door B or door C. Both have goats. If you switch, you lose. 2. The car is behind door B. Monty opens door C, showing a goat. If you switch to door B, you win. 3. The car is behind door C. Monty opens door B, showing a goat. If you switch to door C, you win. Out of these 3 possible scenarios, you will win by switching in 2 of them and lose in just 1. Hence, your chances of winning double when you choose to switch from door A to either of the other doors. This problem highlights the power of probability and the human inclination towards making intuitive, yet often incorrect decisions. The instinct to stick with our first choice may feel more comfortable, even if it goes against statistical reasoning. Many people struggle to grasp this concept at first, as it clashes with our everyday experiences and logic. The Monty Hall problem demonstrates how our cognitive biases can distort our perception of outcomes. reminding us to approach situations with a critical mind and a willingness to challenge our instincts. It encourages us to embrace the unconventional, question what we think we know, and rethink our strategies in various aspects of life. Mathematicians and fans of puzzles have embraced the Monty Hall problem for decades due to its surprising conclusion. Educational resources, forums, and even simulations have been created to visualize this perplexing dilemma, showcasing how switching choices can actually lead to better outcomes. It's a classic example of how easily we can misinterpret probability in complex situations. So, the next time you find yourself making a choice, especially in high-stakes scenarios, remember the Monty Hall problem. Consider the statistics. Challenge your assumptions. Ask yourself whether switching might just tilt the odds in your favor. The world is often more complex than it seems at first glance, and this charming game show puzzle serves as a wonderful reminder of that fact, leaving us not only entertained, but also enlightened. As you draw upon this wisdom, remember that in many scenarios, the unexpected may hold the key to success. Embrace the surprises that life presents and let curiosity steer your decision-making process, for the answers may not always lie where you first look. Pi is one of the most fascinating and enigmatic numbers in the world of mathematics. It is denoted by the Greek letter n, represents the ratio of the circumference of a circle to its diameter. Unlike rational numbers, which can be expressed as fractions and have a repeating or terminating decimal sequence, pi is classified as an irrational number. This means that its decimal representation goes on infinitely without repeating. The mystery of pi has intrigued mathematicians, scientists, and curious minds for centuries. Pi approximates to 3.143159, but that is just the beginning. The digits of pi extend indefinitely, and mathematicians have calculated trillions of digits beyond the decimal point using high-powered computers. However, despite all this computation, no discernible pattern has ever been found in its infinite string of numbers. This characteristic makes pi not only unique, but also a subject of deep interest for both mathematical theory and practical application. The ancient Greeks were among the first to study pi, with Archimedes providing one of the earliest known approximations. He used a method of inscribing and circumscribing polygons around a circle to estimate pi's value. This ingenious technique exemplified the ingenuity of early mathematicians who sought to unlock the secrets of the universe with geometry. As you delve deeper into the world of pi, you will find that it has essential applications beyond mathematics. Whether in physics, engineering, or computer science, pi plays a crucial role. For example, in everyday life, pi is essential when it comes to calculating areas and volumes of circular shapes. Engineers use pi when designing anything from bridges to tunnels, ensuring that circular structures can bear the necessary loads and align properly. Moreover, pi has found its way into many cultures and traditions. In mathematics classrooms around the world, students celebrate March 14th as Pi Day, a festive occasion where they indulge in pies and engage in discussions about this remarkable number. The celebration highlights not just the number itself, but also the joy of discovery and the love of learning that mathematics inspire. In addition to its practical uses, pi has captured the imagination and creativity of artists and writers alike. It has appeared in literature, films, and music, serving as a symbol of the infinite and the unknown. The unending nature of its digits has led some to see it as a metaphor for life's mysteries, an idea that resonates with anyone who has ever pondered the cosmos or the nature of existence. For those who have attempted to memorize pi, you might be amazed by the feats some individuals have achieved. There are people who can recite hundreds, if not thousands, of pi's digits from memory. The current world record for memorizing pi stands at over 70,000 digits. This obsession with its never-ending sequence showcases the relentless pursuit of knowledge and the human desire to conquer the seemingly impossible. As we explore the digits of pi, each new number can feel like uncovering a piece of a vast puzzle. The first few digits, 3.1, 4159, are often the most recognizable, but they lead to an unending array that dots the landscape of mathematics. The beauty of pi lies not just in its numerical form, but also in how it connects various aspects of our world, from the simplest circle drawn on paper to the complex waves of light in quantum physics. In practical situations, when faced with circular tasks, one might use the simplified approximation of 3.14 or even 22.7. However, the true essence of pi lies in its staggering complexity that challenges our understanding. Imagine being tasked with calculating the distance around a perfectly circular pond or designing the beautiful arcs of cathedral ceilings. Pi becomes an indispensable tool in these creative processes. Scientists also rely heavily on pi in fields such as astronomy, where it helps describe the orbits of planets and the vastness of space. The mathematics behind gravitational forces and trajectories harnesses the uncertainty and infinity that pi represents. Its presence permeates equations and models that depict the very fabric of our universe. From a philosophical point of view, pi invites reflection on the nature of infinity and mathematics itself. It reminds us that there are still uncharted territories in both mathematics and science. Even as new technologies and theories evolve, pi remains an ever-present constant, urging us to delve deeper into understanding the world around us. Moreover, pi has a community of enthusiasts that shares the passion of the digits. Online forums, social media groups, and educational websites bring together those fascinated by the infinite series of numbers. Challenges, puzzles, and competitions fuel the excitement, creating a collaborative spirit among math lovers who revel in the beauty that pi offers. In summation, pi is more than just a number. It is a journey into infinity that highlights the elegance of mathematics. Its significance endures, transcending cultures and eras, inspiring countless people to explore the realms of geometry, physics, and beyond. Each time we encounter a circle or calculate an area, we are reminded of pi's remarkable legacy and its unyielding mystery. The next time you see a round object or draw a circle, take a moment to appreciate the connection to this extraordinary number. While its digits may never yield to a simple pattern, the wonder of pi carries on, inviting curiosity and exploration for generations to come. And as we continue to probe its depths, we find that sometimes the most profound truths are those that remain just out of reach, shimmering with the allure of the infinite. Mathematical knot theory is a fascinating area of study that delves into the properties and structures of knots in a systematic and theoretical way. At its core, knot theory examines how loops can be intertwined, tangled, or tied, and how these configurations can be described mathematically. You might wonder why the concept of knots, something so commonplace in everyday life, has intrigued mathematicians and scientists alike. To begin, let us visualize a simple knot. Picture a shoelace tied into a bow. This seemingly trivial object can be analyzed in terms of its topology, which is a branch of mathematics that studies properties that remain unchanged even when the shape is distorted. In knot theory, a knot is defined as a closed, non-intersecting curve in three-dimensional space. When we tether a piece of string to form a loop, we create a knot. However, not all loops are knots. An untied loop, for instance, is merely a circle and does not present the complexity that a true knot does. One of the many intriguing aspects of knot theory is its surprising connections to various scientific fields. For example, in biology, researchers have discovered that knot theory can help explain the structure of DNA. DNA is composed of two strands that twist and coil in complex ways and form supercoils. When biologists analyze DNA structures, they often employ knot theory to understand the knot-like shapes that these molecules can take. This connection between mathematics and biology is not just an academic exercise. The study of these knots has practical implications in gene editing and understanding genetic diseases. Turning to chemistry, knot theory finds relevance in the field of molecular chemistry. Molecules can become entwined in ways reminiscent of knots. For instance, in the study of proteins, knot theory can help illustrate how certain proteins fold and function. Some proteins possess knot-like configurations that are vital for their activity. The understanding of these molecular knots can provide insight into how proteins interact with one another and how they contribute to biological processes. Physics also integrates knot theory in compelling ways. In particular, the field of quantum physics has seen applications of knot theory in the study of particle physics. Here, researchers have discovered that the concept of knots can help model the behavior of particles under various conditions. The entangled states of particles can be thought of in terms of knots, providing a visual and mathematical framework to study their interactions and transformations. Mathematics itself becomes increasingly interesting as one dives deeper into knot theory, revealing a rich tapestry of concepts and structures. For example, mathematicians have defined various types of knots, such as prime knots, which cannot be decomposed into simpler knots, and composite knots, which are formed by tying two or more prime knots together. Analyzing these different classifications can unlock new understanding within the mathematical community. One of the classic problems in knot theory is the knot classification problem. This problem involves determining whether two knots are equivalent, meaning they can be transformed into each other through continuous deformations without cutting the string. This process employs various knot invariants, quantities that remain the same regardless of how the knots are manipulated. For example, the crossing number of a knot, which counts the minimum number of crossings in a diagram representation, serves as a useful invariant. In recent years, mathematicians have developed new computational methods and techniques to analyze knots more efficiently, allowing for greater exploration of complex knots and their properties. This has led to the discovery of many intriguing examples and relationships among various knots. As a result, knot theory continues to evolve, merging classical mathematical insights with modern computational power. The implications of knot theory extend even into the realms of art and philosophy. Artists have drawn inspiration from the visual elegance of knots, creating sculptures and works that resonate with mathematical beauty. At the same time, philosophers ponder the existence and significance of tangling and untangling as metaphors for human life, relationships, and experiences, drawing parallels between the study of knots and the knots present in our personal narratives. The connections between knot theory and various fields remind us of the intrinsic unity of knowledge. Mathematics, science, and art are not isolated domains. They are intertwined in profound ways, much like the knots themselves. The exploration of mathematical knots invites a sense of wonder and curiosity, encouraging the pursuit of connections beyond immediate observation. As one contemplates the seemingly simple act of tying a knot, it becomes clear that there are layers of complexity and nuance waiting to be unraveled. From the everyday experiences of tying shoelaces to the intricate designs of DNA and complex interactions in physics, mathematical knot theory bridges the gap between pure abstraction and practical application, revealing the underlying fabric of our universe through the lens of knots. Thus, the study of knots is not merely about understanding a mathematical concept. It represents an invitation to engage with the world in a fresh and enlightening way. The intricate dance of threads, the profound implications in science, and the beauty found in their forms encourage a deeper appreciation for both mathematics and the interconnectedness of all knowledge. Exploring these connections not only enriches our understanding, but also fosters a greater sense of curiosity and awe for the complexity that surrounds us. As we continue to delve into the world of knot theory, we discover more than just mathematical principles. We uncover the threads that weave together the universe itself. Magic hexagons are a captivating concept in the world of mathematics and number arrangements. While most might be familiar with magic squares, which are square grids filled with numbers that result in the same sum for each row, column, and diagonal, magic hexagons take this idea and explore it in a hexagonal format. These intricate patterns provide not only a mathematical challenge, but also a beautiful representation of symmetry and balance. At its core, a magic hexagon is made up of numbers arranged in a hexagonal shape. The goal is to fill this hexagon with distinct integers, such that the sums of the numbers in each row, as well as in each diagonal, yield the same magic constant. This magic constant can be intriguing as it places constraints on how numbers can be organized to create harmony within the shape. The most famous magic hexagon is known as the order 3 magic hexagon. It contains 19 cells arranged in a hexagonal pattern. The numbers used in this arrangement typically range from 1 to 19. When correctly filled, the magic constant for this hexagon is 38. Achieving this means that each row and diagonal sums to 38, resulting in a visual and numerical symphony. To appreciate the beauty of magic hexagons, visualize their structure. Picture a large hexagon in front of you. At its center, you place the largest number, in this case, 10, which serves as the heart of the hexagon. Surrounding it, you place the next set of numbers, carefully ensuring that each row and each diagonal ultimately culminates in the same sum. This involves trial and error, intuition, and a keen sense of spatial awareness. Imagine taking a blank sheet and sketching this hexagonal shape. You begin by writing the number 10 in the middle. Next, you need to balance the surrounding numbers. You could position 1, 2, and 3 below it, while placing 4, 5, and 6 on one side and 7, 8, and 9 on the opposite side. The unique aspect of magic hexagons is that the arrays can vary substantially in appearance, yet still maintain the core magical property of equality in sums. What makes these hexagons particularly mesmerizing is the interplay between geometry and arithmetic. As you engage in creating these patterns, you not only exercise your mathematical skills, but also unleash your creativity. You find yourself immersed in the process of checking the sums, exploring where you may need to adjust a number, or how shifting a single unit can alter the entire balance. Consider how this differs from traditional magic squares. The square has fixed rows and columns that operates neatly within its grid. The hexagon, however, like nature itself, embraces a more dynamic form. It reflects the intricacies of natural formations around us. Think of honeycombs, which are a manifestation of hexagonal symmetry found in nature. These hexagonal patterns are efficient and strong, much like the structure of a magic hexagon, where each number holds importance and contributes to a greater whole. As mathematicians have explored these hexagonal patterns, they have uncovered various configurations. While most studies focus on smaller orders, the hunt for larger magic hexagons continues to intrigue number enthusiasts. Larger arrangements present even more complex challenges due to the increased number of cells and potential combinations. The larger the hexagon, the more intricate and engaging the puzzle becomes, demanding greater logical reasoning and creative thinking. Additionally, the symmetries observed in magic hexagons can be compared to those found in other mathematical fields, like symmetry in algebra or geometry, showing a universal principle of balance. Recognizing the interconnectedness between different areas of mathematics can deepen one's appreciation of such mathematical constructs. Whether one is an avid mathematician or just a curious mind, delving into the world of magic hexagons can ignite a sense of wonder. This exploration is not merely an intellectual pursuit. It is an invitation to immerse yourself in patterns, possibilities, and the sheer beauty of number. Visualize a gathering of desks in a classroom where students work collaboratively to create their own magic hexagons. Picture them passionately sharing their discoveries, debating over placements, and explaining their thought processes. In this environment, learning becomes a communal experience, enriched by shared insights. Everyone involved develops not only numerical skills, but also enhances critical thinking and problem-solving abilities. As you engage with magic hexagons, take note of how your understanding evolves. What starts as a logical challenge transforms into a creative expedition. You might even feel a rush of excitement as the pieces begin to fit into place, as if you were uncovering a hidden treasure within the structure of numbers. As interest in these hexagonal phenomena continues to grow, mathematicians even delve into their applications beyond mere puzzles. Some researchers are exploring how these structures can help model certain real-world phenomena, echoing how often mathematics provides insights into nature's working. The reach of these magic instances feels boundless, weaving connections between numerical creativity and understanding the universe around us. Ultimately, whether you find yourself drawing these patterns, teaching them to others, or simply contemplating their elegance, magic hexagons embody an enchanting blend of art and science. So as you venture further into the intriguing world of numbers, remember that magic hexagons invite you to experience the beauty of balance, the thrill of discovery, and the joy that mathematics can bring to curious minds of all ages. Imagine a puzzle that has fascinated mathematicians and puzzle enthusiasts for over a century. This captivating enigma is known as the Tower of Hanoi. Picture 3 pegs, standing tall and proud, with a set of discs of varying sizes neatly stacked on one of them. The smallest disc is placed at the top, and the largest disc occupies the base, creating a beautiful yet precarious tower of discs. The challenge in the Tower of Hanoi is to move all the discs from the starting peg to a target peg, but there are strict rules you must follow. Only one disc can be moved at a time, and you can never place a larger disc on top of a smaller one. This simple yet compelling setup creates a scenario that runs deeply into the realms of mathematics and logic. Let's delve deeper into the rules that govern the Tower of Hanoi. First, you can only move one disc at a time. This rule invites you to think critically, as each move influences your next step. Second, you cannot place a larger disc on top of a smaller disc. This constraint adds an additional layer of complexity to the puzzle, challenging your understanding of arrangement and order. Now, let's explore the process of solving this puzzle. When faced with a situation involving the Tower of Hanoi, a remarkable aspect emerges: recursion. This concept is evident in problem solving, where the same solution applies repeatedly on scaled-down versions of the problem until reaching a base case. Think of it this way. If you have 3 disks to move, your first move might involve transferring the smallest disk to the target peg. Next, you would focus on moving the remaining larger disks, which presents a smaller version of the original problem. Visualize the process. You start with 3 disks on the first peg. To transfer all 3 disks to the second peg, you first need to move the top 2 disks to the third peg, using the second peg as an intermediary. Once those 2 disks are safely transferred, you are left with the largest disk on the first peg, allowing you to move it directly to the second peg. Finally, you can move the 2 disks from the third peg to the second peg, following the same rules. Now, let's see the mathematical aspect of the Tower of Hanoi. The minimum number of moves required to solve the puzzle can be calculated using a simple formula. For n disks, the number of moves required is 2 raised to the power of n minus 1. So, if you have 3 disks, the minimum number of moves to solve the puzzle is 2 to the power of 3, which equals 8 minus 1, resulting in 7 moves. This exponential growth showcases how quickly the complexity of the puzzle escalates with each added disk. Now imagine this puzzle with more than just 3 disks. Each additional disk adds layers of complexity. For 4 disks, it takes 15 moves, and for 5 disks, 31 moves. The challenge increases rapidly as you pile on the disks, invoking your problem-solving and logical reasoning skill. Apart from being a simple puzzle, the Tower of Hanoi has enriched various fields such as computer science, mathematics, and cognitive science. It serves as an excellent example of recursive algorithms in programming, guiding young coders in structuring their functions. When writing a function to solve the Tower of Hanoi, programmers often use recursion, where the function calls itself to process a smaller subset of the problem until it reaches the simplest scenario. This beautiful relationship between a seemingly simple puzzle and complex mathematical principles alerts us to the interconnectedness of different domains of knowledge. The Tower of Hanoi is more than just a game. It is a profound illustration of strategy, logic, and systematic thought. Imagine sharing this puzzle with friends or family, gathering around to see who can solve it the fastest. The competitive element, paired with the challenge of adhering to the rules, creates an engaging atmosphere. The beauty of the Tower of Hanoi lies not just in its solution, but in the journey you take to uncover it. As we explore various problem-solving techniques, the Tower of Hanoi remains a timeless tool for unraveling deeper concepts. The elegance of this puzzle showcases how mathematics can step outside the classroom, inviting learners to engage with concepts in a playful and intriguing manner. Whether you are a novice puzzler or a seasoned mathematician, this game offers a blend of challenge and satisfaction. In a world where new puzzles and enigmas are constantly emerging, the Tower of Hanoi holds a special place in hearts and minds, reflecting the art of strategic movement over rigid constraints. It invites us to consider the power of deductive reasoning and the importance of methodical thinking. So, as you take a moment to appreciate the simple pegs and disks, consider the vast mathematical landscape that the Tower of Hanoi represents. Within this seemingly elementary puzzle lies a universe of recursive strategies waiting to be discovered. And who knows, by engaging with the Tower of Hanoi, you might just unlock new ways of thinking about problems in your everyday life, leaving an imprint of logic and creativity in your mind. Whether it's about moving disks or solving everyday challenges, the principles remain the same. Think critically, plan ahead, and embrace the beauty of recursion. Let this ancient puzzle serve as your guide, illustrating how structured thought can lead to elegant solutions and ignite a passion for problem-solving within you. The Tower of Hanoi remains a captivating puzzle for all ages, bridging generations through its timeless appeal, inviting each of us to step into the world of logic and strategy. Tessellations are fascinating patterns that cover a surface without any gaps or overlaps. Imagine a beautifully tiled floor where each piece fits perfectly with the others. This concept transcends mere decoration and steps into the realm of mathematics, art, and nature. Let's explore this captivating world of tessellations and tiling. To start, consider the simplest form of tessellation, regular polygons. A classic example is a square tile. When many square tiles are placed side by side, they create a uniform pattern that extends infinitely. You can visualize this layout in your kitchen or bathroom, where the tiles are arranged to create an aesthetically pleasing floor. The properties of shapes come into play here. Squares, triangles, and hexagons are regular polygons that can form perfect tessellations because they can fill space without leaving any gaps. Hexagons, for instance, are quite remarkable. Think about honeycombs. The hexagonal shapes provide a unique advantage in nature, allowing bees to store honey efficiently. This arrangement also utilizes space optimally while maintaining structural integrity. This is an excellent demonstration of how naturally occurring patterns can be both practical and beautiful. Now, diametrically opposed to regular tiling, we have irregular tiling. Imagine a mosaic created with pieces of varying shapes, sizes, and colors. This kind of tessellation offers a dynamic aesthetic where every piece contributes to a larger picture, often involving intricate designs and themes. Artists have leveraged this style for centuries, creating stunning artworks that catch the eye. Take a moment to think about the glorious mosaics found in ancient Roman architecture or the vibrant tiles in Moroccan decor. Each piece is unique, yet contributes to a cohesive visual experience, a testament to the creativity of the artist. Moving beyond these shapes, we encounter non-periodic tessellations, the most famous being Penrose tiling. This unique form of tessellation uses a set of tiles that never repeats, creating an infinitely intricate pattern. Penrose tiles come in two shapes that interlock in a way that defies repetition. This concept can cause a bit of a brain workout, as it blurs the lines of what we generally consider tessellation. The patterns created are mesmerizing, with an almost hypnotic quality that draws you into their depths. This beautiful complexity can be found in various artworks and designs, making them a favorite among mathematicians and artists alike. Tessellations are not merely confined to tiles or floors. They can be found in nature as well. Nature's designs often showcase tessellation effectively. Take, for instance, the intricate patterns of leaves or the scales of fish. The design of a pineapple's exterior reveals an astonishing tessellation of hexagonal arrangements, perfectly suited to its growth process. Nature thrives on these efficient patterns, demonstrating yet another angle on the vast topic of tessellations. Now, consider the fascinating mathematical side of tessellations. Mathematicians study these patterns not only for their aesthetic appeal but also for their structural applications. Tessellation helps understand patterns in geometry, symmetry, and even fractals. The study of these formations leads to discoveries in areas such as crystallography, art, and design. One can explore how these patterns function in complex mathematics, drawing connections to fields like computer graphics and architecture. Tessellating patterns inspire architects too. Throughout history, buildings have been designed to utilize tessellation in charming ways. Think about vaulted ceilings and decorative tiling in historical buildings. The flexibility of shapes and their fitting possibilities have inspired groundbreaking architectural designs. The Alhambra Palace in Spain, with its stunning Islamic mosaics and geometric patterns, stands as a timeless exemplar of how elegant tessellation can enrich architectural beauty. Moreover, tessellations have also found their way into the field of art. Artists like M.C. Escher have crafted stunning works that play with the viewer's perception using tessellated forms. Escher's pieces often feature creatures morphing into one another, seamlessly transitioning between shapes and forms. He employed mathematical principles in art to create illusions that challenge perspective. Such works offer a fascinating insight into the interrelation between mathematics and artistic creativity. Let's not forget about the digital realm, where technology allows for the creation of tessellations that can adapt and transform. With advanced software, artists can design intricate tessellated patterns that would be exceedingly difficult to create by hand. The fluidity of digital design means that tessellations can be animated, upgraded, and customized. This way, we see how technology amplifies the human imagination, bringing forth creations that resonate with both complexity and beauty. Finally, we arrive back to the concept of patterns in everyday life. Invitations, wall art, fashion, and home decor often employ tessellated designs. You may see repetitive patterns adorning wallpaper or clothing, each playing a role in the overall aesthetic statement. This approach adds depth and character, providing a visual rhythm that enhances our surrounding. Tessellations invite us to examine our environment from a different perspective. They serve as reminders that often beauty lies in the repetition and arrangement of simple shapes. The joy of discovering a new pattern, whether on a tiled floor or in nature, speaks to our innate curiosity. It captures the imagination and elevates our appreciation for both art and science. In conclusion, the study of tessellations spans far beyond simple designs and patterns. From the geometry behind regular shapes to the mesmerizing complexity of Penrose patterns, tessellations reveal a world that intertwines art, mathematics, and nature. Exploring these concepts can open a doorway to a richer understanding, where we may find harmony in patterns and beauty in configurations. The next time you encounter a tiled surface or a patterned wall, take a moment to pause and appreciate the intricate organization of pieces that transforms the mundane into something remarkable. Each form tells a story, each repetition offers a new perspective, and there is always more to discover within this intricate tapestry of shape. Gödel's incompleteness theorems are two of the most significant results in mathematical logic and the philosophy of mathematics. They were introduced by Kurt Gödel in the early 20th century and revolutionized our understanding of the foundations of mathematics. These theorems demonstrate limitations inherent in every logical system capable of expressing basic arithmetic. Understanding them not only sheds light on the nature of mathematical proofs, but also raises profound questions about truth and knowledge. The first of Gödel's theorems states that in any consistent formal system that is powerful enough to encapsulate basic arithmetic, there exist statements that are true, but cannot be proven within that system. Imagine a mathematical language that has its own rules, axioms, and theorems. Gödel illustrated that no matter how comprehensive this system might be, there will always be formulas that are true but elude confirmation through the system's axiom. This is akin to trying to find a missing piece of a jigsaw puzzle that just does not fit, no matter how hard one tries. To grasp this theorem, consider a more everyday concept. Imagine a set of instructions for a recipe that appears to cover all possible variations of a dish. However, you discover a delicious way to prepare it that isn't mentioned in the recipe at all. No matter how well the recipe is written, it cannot account for every culinary possibility. In the same way, Gödel's first theorem tells us that formal mathematical systems may also overlook certain truths. Moving to Gödel's second theorem, it states that such a system cannot prove its own consistency, provided it is indeed consistent. This means that if you have a logical system designed to handle arithmetic, it cannot confirm that its own rules do not lead to contradictions. To simplify, think of a company conducting an internal audit to affirm that it follows all rules and procedures correctly. However, the company cannot conduct this review without relying on the same rules it is trying to validate. In essence, it faces a paradox similar to that found in Gödel's second theorem. Gödel used a clever technique known as arithmetization to accomplish these theorems. He transformed statements, proofs, and even the processes of proving into numbers. Among his most extraordinary contributions is the creation of a self-referential statement that essentially says, "This statement cannot be proven true." If this statement were to be proven true, it would create a contradiction, as it claimed it cannot be proven. If it were false, it suggests there is a true statement that cannot be proven, demonstrating the very essence of Gödel's findings. These results have far-reaching implications that go beyond the realm of mathematics. They challenge the notion of complete knowledge, raising questions about what it means to know something. If there are truths we cannot reach through formal proofs, what does that imply about other fields? In philosophy, ethics, and even the sciences, Gödel's theorems invite deeper reflection on the limits of human understanding and the nature of reality itself. Gödel's work invites us to consider the role of intuition versus formal logic. In many disciplines, an intuitive grasp of truth often precedes formal analysis. For instance, great artists may convey emotions in their work that transcend explicit explanations, similarly suggesting that not all truths can be laid out logically. This interplay between what can be formally verified and what is felt or perceived touches upon the arts, humanities, and sciences alike. In computer science, Gödel's theorems also hold significance. They suggest that there are limits to what can be computed or decided through algorithms. Problems that are undecidable, or for which no algorithm can be constructed to provide an answer, stem from the same philosophical roots laid out by Gödel. This idea permeates discussions about artificial intelligence, where the capacity to understand or simulate decision-making processes raises ongoing debates about the boundaries of machine intelligence. Gödel also had a profound influence on mathematicians and logicians who followed him. The implications of his theorems invited explorations into non-Euclidean geometries, set theories, and various mathematical paradoxes. Scholars continue to dive into the dimensions of his findings, exploring their relevance to modern mathematics, scientific theory, and even existential musings about the human condition. These discussions can lead to broader inquiries about certainty and uncertainty in our lives. We often experience moments of insight or understanding that seem to come from nowhere, reminding us that not all truths can be neatly packaged or formally deduced. Just as Gödel showed that mathematical systems can be incomplete, our personal truths are often nuanced and layered. Life is full of complexity, and navigating that complexity involves recognizing and accepting that not everything is knowable. Gödel's incompleteness. Theorems challenge a long-standing belief in a complete and consistent mathematical system. They underscore the limitations of formal reasoning while encouraging us to embrace the mysteries of both mathematics and life. Just as Gödel opened doors to new avenues of thought and logic, his insights continue to inspire explorations into our understanding of knowledge, creativity, and the ever-elusive nature of truth. In summary, Gödel's incompleteness theorems illustrate that within any logical system, especially those complex enough to include arithmetic, there exist truths that cannot be proven within the framework of that system itself. His work prompts a reevaluation of the limits of knowledge, the power of intuition, and the complexity of understanding, a legacy that resonates across multiple disciplines, enriching our appreciation for the profound nature of both mathematics and existence. As we ponder the breadth of what we can know and what will forever remain elusive, Gödel's insights linger in our thoughts, reminding us that the quest for understanding is a journey without finite bounds. The Gaussian distribution, often referred to as the bell curve, is one of the most significant concepts in statistics and probability theory. This distribution plays a crucial role in various fields, including psychology, finance, biology, and more. Its characteristics and implications are profound, shaping our understanding of randomness and variation in the world around us. To begin with, let's visualize the shape of the Gaussian distribution. Imagine a smooth, gently rising and falling curve that forms a hill. The peak represents the averages or means of a data set. As you move away from the center, the values become less frequent, creating a beautiful symmetry on both sides. This symmetrical shape is a hallmark of the Gaussian distribution, making it unique compared to other distribution forms. The Gaussian distribution is defined by two parameters, the mean and the standard deviation. The mean provides the center of the distribution, indicating where most of the data points lie. The standard deviation, on the other hand, offers insight into how spread out the data is. A smaller standard deviation suggests that the data points are clustered tightly around the mean, creating a narrow, tall bell curve. In contrast, a larger standard deviation indicates a wider, flatter bell curve, showing that the data points are dispersed more broadly. One interesting aspect of the Gaussian distribution is how often it appears in real-world scenarios. For example, consider height. If you measure the heights of a large number of people, you will likely find that most people fall around an average height, with fewer individuals being significantly shorter or taller. This results in a bell-shaped curve when the data is graphed. The same phenomenon can be observed in intelligence testing. Most people score near the average IQ, with progressively fewer people scoring very low or very high, creating yet another instance of the Gaussian distribution. In addition to human characteristics, the Gaussian distribution can also be observed in natural processes. Think about the distribution of errors in measurements. Due to randomness, the errors in repeated measurements generally follow a Gaussian distribution, centralizing around the true value. This phenomenon is known as the central limit theorem, which states that the means of samples of a population drawn from any distribution will tend to form a Gaussian distribution as the sample size grows. This powerful theorem underscores the versatility and importance of the Gaussian distribution in statistics. The implications of the bell curve extend to various other examples, such as the distribution of test scores in educational settings. When educators assess students, their scores typically aggregate around the average, with few students attaining scores that are significantly lower or higher. This bell curve shape allows educators to identify performance, set benchmarks, and understand the overall learning outcomes of their students. In finance, The Gaussian distribution is pivotal in risk analysis and modeling returns on investments. Many financial theories and models, including those used in portfolio management, assume that asset returns will follow a normal distribution. This assumption allows financial professionals to assess risk and make predictions based on historical data. However, it should be noted that while the Gaussian distribution serves as a helpful guide, real-world financial returns can often demonstrate significant deviations from this theoretical model. In biology, the Gaussian distribution helps explain various phenomena, including the distribution of traits in populations. For instance, consider the width of a certain flower petal among a large population of flowers. Measurement of this trait would likely reveal a bell-shaped curve, suggesting that most flowers have petal widths near the average, with fewer instances of extreme widths. Interestingly, the Gaussian distribution is also related to concepts of probability. The area under the curve of the bell shape represents the total probability, which sums to 1. This means that the entire universe of possible outcomes is accounted for under this curve, providing a complete view of the data at hand. The beauty of this distribution lies not just in its mathematical formulation, but also in how it captures the essence of randomness in nature. The practical applications of the Gaussian distribution are vast and varied. You might find it in quality control and manufacturing, where the distribution helps track variations in product dimensions. Imagine a factory producing a complex component. The dimensions must align closely with specifications for the product to function correctly. Using techniques derived from the Gaussian distribution, quality control engineers can identify acceptable ranges and detect anomalies in production. Moreover, researchers harness the Gaussian distribution to analyze phenomena in the natural sciences. In meteorology, for example, the distribution of temperature fluctuations throughout the year might resemble a bell curve, aiding climatologists in understanding weather patterns. Another fascinating example features the neurological responses within the field of psychology. Human reactions to stimuli can also follow a Gaussian distribution. Consider a psychological study examining response times among participants in a reaction time test. As dictated by the principles of the bell curve, most individuals might respond within a certain time frame, with fewer individuals responding very quickly or very slowly. Despite the myriad benefits and applications, it is essential to recognize that not all phenomena align perfectly with Gaussian distributions. For example, financial returns can often exhibit skewness or differences in kurtosis, diverging from the bell curve's assumptions. Similar variations can occur in other fields where extreme values might skew the overall distribution. This reality requires careful consideration when utilizing the Gaussian distribution for analysis and decision-making. In conclusion, the Gaussian distribution, with its iconic bell-shaped curve, is a central pillar in the world of statistics. Its widespread appearance in various fields, from biology to finance, highlights its significance in explaining randomness and variation in natural and man-made systems. Whether you are measuring human traits, assessing financial risks, or analyzing natural phenomena, understanding the Gaussian distribution provides vital insight into the underlying patterns that govern our world. This concept not only enriches scientific discussions, but also deepens our appreciation of the intricate, often beautiful order that can emerge from randomness. Conway's game of life is a fascinating concept that combines mathematics, biology, and computer science to create intricate behaviors from very simple rules. Imagine a vast, infinite grid composed of countless squares. Each square can either be alive or dead, represented as a black or white square, respectively. What sounds simple at first quickly reveals a complex world of patterns and interactions. The magic begins with just a handful of initial configurations. These cases can spring to life with a variety of behaviors, showcasing how complicated phenomena can emerge from basic instruction. John Horton Conway, the British mathematician who created this intriguing game in 1970, designed it with rules that govern how these squares interact with each other. Each square's fate is determined by its 8 neighbors, those squares that are directly adjacent, including diagonals. Let's delve into the rules that dictate how life and death unfold on this grid. If a living cell is surrounded by fewer than 2 living neighbors, it dies, much like a solitary existence, leading to a gradual fading away. Conversely, if a living cell has more than 3 neighbors, overcrowding leads to its demise. But in a sweet spot of 2 or 3 live neighbors, life flourishes, allowing that cell to continue its existence. Lastly, a dead square springs to life if exactly 3 live neighbors surround it, a phenomenon akin to a sudden spark of creation. This simple set of rules generates an astounding variety of patterns. Some of these patterns oscillate back and forth, while others glide through the grid in a mesmerizing dance known as gliders. For instance, gliders are a small arrangement of cells that shifts diagonally across the grid, leaving a trail of life in its wake. Such patterns can be seen as tiny ships sailing through the ocean of cells. Another intriguing aspect involves still lifes, which are configurations that remain unchanged over multiple generations. An example is the classic block, a 2x2 square that sits quietly without changing. Still lifes provide stability and order in an ever-evolving environment, forming the backbone of more intricate creatures. Then, we have oscillators, which display periodic behavior by changing back and forth over generations. A popular oscillator is the blinker, which alternates between a vertical and horizontal line of cells. Observing these transformations evokes a sense of rhythm as patterns pulse across the grid, like a heartbeat echoing through the cosmos. What makes Conway's game so enthralling is its ability to simulate life's complexities without requiring any biological input or realism. It emphasizes how order can arise from chaos, echoing philosophies found in nature and society. For example, patterns established in early generations can grow and lead to entirely new formations in subsequent generations, much like how simple actions in a community can create waves of change over time. Despite the apparent simplicity of the rules, even experienced players can be surprised by the game's outcomes. Some configurations lead to patterns that reproduce themselves or even create other patterns, showcasing the intrinsic creativity and unpredictability found in life itself. As new structures emerge, the grid transforms into a living artwork, with brushes made of squares dancing against the canvas of infinity. A remarkable feature of the game of life is that it can exhibit properties of Turing machines, suggesting that it can compute anything that a standard computer can, given enough time and space. This observation has made Conway's creation a cornerstone in the field of cellular automata and mathematical theory. Researchers explore its implications in artificial life, complexity theory, and even philosophical inquiries about existence and the nature of life. Players of Conway's game often find themselves caught in a perpetual loop of experimentation, observing different patterns and trying to predict their evolution is part of the thrill. Many enthusiasts spend their time uncovering new configurations that may lead to unexpected behaviors. The communities that have formed around this game often share findings, creating a network of knowledge and creativity that continues to evolve. As the grid expands, players can try different initial states to observe diverse outcomes. Observing how different starting points lead to entirely different endings invites a sense of wonder. A cluster of few squares in one corner can unfold into a sprawling metropolis of life and activity elsewhere on the grid, illustrating how the smallest changes can yield massive impacts. It is also interesting to note that Conway's game of life has inspired various artistic interpretations, ranging from digital representations in films to physical artworks that capture the essence of cellular automata. Artists and programmers alike have utilized these concepts to create visual displays that demonstrate the beauty and complexity of life arrangements on a simple grid. In conclusion, Conway's game of life represents a beautiful intersection of simplicity and complexity. Through its rules, we can observe lively interactions in an otherwise static environment, leading to endless possibilities and outcomes. Whether a casual player or a serious researcher, there's always something new to explore and discover within this timeless exploration of patterns in life. In the heart of East Prussia, now known as Kaliningrad, lies a fascinating historical puzzle that has intrigued mathematicians for centuries. The puzzle revolves around the city of Königsberg, which was crisscrossed by several rivers, creating an intricate landscape of bridges. Imagine walking through a town with its picturesque rivers and pathways, where your goal is to traverse each bridge exactly once without retracing your steps. This seemingly simple challenge gave rise to the fundamental concepts of graph theory. In the 18th century, Königsberg had 7 bridges in total, connecting the 4 land masses that were separated by the Pregel River. The layout of these bridges was such that citizens found it impossible to walk through the city and cross each bridge only once. It was a common pastime for locals to try to solve this intriguing problem. However, no matter how they attempted the challenge, they always ended up having to cross at least one bridge more than once. This puzzling scenario caught the attention of a brilliant mathematician named Leonhard Euler. In 1736, Euler decided to take on the challenge posed by the bridges of Königsberg. Rather than approaching it as a geographical or physical puzzle, he transformed it into an abstract mathematical problem. Euler's insightful approach led him to represent the land masses as points or vertices in a diagram, and the bridges as lines or edges connecting these points. This marked the beginning of graph theory, a branch of mathematics that explores networks of vertices and edges. To understand Euler's perspective, envision the 4 land masses of Königsberg as dots on a piece of paper. The bridges become connections, linking these dots. Euler soon realized that for anyone to traverse each bridge exactly once, certain conditions needed to be met, particularly regarding the number of times each vertex is connected by edges. He identified that for a solution to exist, each landmass must either have an even number of connections or have at most 2 landmasses with an odd number of connections. In the case of Königsberg, however, all 4 landmasses had an odd number of connections, making it impossible to cross each bridge once without retracing steps. Euler's groundbreaking work on this problem not only solved the puzzle, but also established a foundation for future explorations in mathematics and computer science. His findings laid the groundwork for understanding networks, paving the way for advancements in various fields, including transportation, telecommunications, and social networks. The implications of his work are far-reaching, as it can be applied to anything from optimizing routes for delivery trucks to analyzing social interactions among individuals. This exploration of Königsberg's bridges highlights the beauty of mathematics as a tool for understanding and simplifying complex problems. Euler's transformation of a real-world issue into a mathematical abstraction showcases how curiosity and creativity can lead to significant discoveries. His approach illustrates the power of visualization in problem solving. By reducing the physical world to symbols and connections, he unlocked a new realm of mathematical thinking. As the centuries have passed, the puzzle of the Bridges of Königsberg continues to inspire mathematicians, educators, and puzzle enthusiasts alike. It serves as a classic example of how a seemingly simple question can evolve into a complex inquiry, ultimately leading to remarkable insights. Euler's bridge problem not only contributed to the development of graph theory, but also changed how we think about problems involving networks and connections. In modern times, the ideas stemming from Euler's work have only become more relevant. Today, we are surrounded by networks in daily life, from the internet to social networks, logistics, and urban planning. Each of these applications relies on the principles established by Euler. For instance, when mapping the most efficient route for delivery trucks, graph theory provides the framework for optimizing paths and minimizing costs. Moreover, cities across the globe face similar challenges to that of the inhabitants of Königsberg. Urban planners and architects must consider the flow of movement and connectivity within their designs. By applying the concepts derived from Euler's investigations of the Königsberg bridges, they can create efficient, interconnected spaces that enhance the quality of life for residents. Reflecting on the story of the Bridges of Königsberg reveals much about the essence of problem solving. It encourages us to look beyond conventional approaches and seek alternative perspective. When faced with a challenge that seems insurmountable, one might remember Euler's creative brilliance. The history of the Bridges of Königsberg embodies the spirit of inquiry, a reminder that even the simplest questions can lead to profound discoveries. Visiting Kaliningrad today, one might find themselves standing at the banks of the Pregel River, pondering the intricate web of bridges that once existed. The legacy of the bridges continues to resonate, inviting people to explore the intersection of history, mathematics, and human ingenuity. The story serves to inspire future generations to embrace challenges and transform them into opportunities for growth and understanding. In summary, the Bridges of Königsberg were not just a geographical curiosity. They were a catalyst for one of the most significant developments in mathematics. Through Euler's innovative thinking, a local puzzle transformed into a foundation for understanding complex networks that affects countless aspects of modern life. As we reflect on this vibrant piece of history, let it motivate our own explorations into the world of connections, inviting us to uncover the mysteries that lie within our own complexities. The birthday paradox is a fascinating concept in probability that often catches people by surprise. Imagine you are in a room with 22 other people, making a total of 23 individuals. At first glance, you might think that the chances of two people sharing the same birthday would be low, given that there are 365 days in a year. Surprisingly, though, in this group of 23, there's actually about a 50% chance that at least two people have the same birthday. This phenomenon raises eyebrows and stirs curiosity as it challenges our intuitions about probability. To better understand this concept, let's break it down. The idea is not so much about the probability of your birthday aligning with someone else's. Instead, it centers around the number of pairings that can be made within a group. In a gathering of 23 people, you can create many pairs of birthdays. Specifically, there are 253 unique pairs of people in this group. Each of these pairs offers a potential opportunity for a shared birthday. As a thought experiment, consider a smaller group first. If there are just two people, the chance that they share a birthday is clearly very low. The first person can have their birthday on any day of the year, and the second person to share a birthday would need to have their birthday fall on that same specific day. The chance of that happening is 1 in 365. When 3 people are involved, things begin to change slightly. The first person can still choose any day. The second person now has a 1 in 365 chance to match with the first, and the third person also has a 1 in 365 chance of matching either of the first two. You might expect these numbers to indicate how quickly the probability grows, but the increase is slow and subtle. However, as you continue adding more people to the group, the number of opportunities for shared birthdays increases dramatically. To visualize this concept, imagine each person having a colored ball that represents their birthday. If 23 people each have a ball of a different color, it's easy to see how unique they are. But as new colors get introduced, the combinations and overlaps increase. It is this intersection of possibilities that leads to the surprisingly high probability of shared birthdays in larger groups. Let's consider a real-world analogy. Think of a lottery draw where you have a group of players. Each person picks a set of numbers, and the more players you have, the greater the chance that someone will select the winning combination. In essence, this is what happens with birthdays. Adding more people to the mix creates more opportunities for coincidences. Many people find the birthday paradox astonishing because intuitively, it feels as if such coincidences should be rare. But mathematics suggests otherwise. Statistically, in a group of just 23 people, a 50% chance for matching birthdays reflects how our intuition can mislead us. It demonstrates a key principle in probability, that large sample sizes can lead to unexpected results. You may ask why this exact number, 23, is so significant. A group size of 23 is the tipping point where the odds cross the boundary from less than 50% to more than 50%. This means that in gatherings or parties with just a few close friends, there is still a significant likelihood that someone shares a birthday with another. Exploring further reveals that the probability grows even larger with each additional individual. If the group size increases to 30 people, the probability rises to around 70%. The more people you add, the more the likelihood balloons. By the time you assemble a group of around 50 people, you start to reach probabilities of over 97% that at least 2 people will share a birthday. This fascination spans beyond simple party conversations. The birthday paradox highlights statistical truths in various fields, including computer science, cryptography, and social sciences. It has implications for how we design systems and understand data points within large populations. Imagine a classroom where you are trying to figure out how many students might share a birthday. Using the principles of the birthday paradox, a teacher might find that preparing for a celebration could be much simpler than expected. The same logic applies in various other scenarios. Any gathering of people opens up a world of possibilities regarding shared commonalities. So, next time you find yourself among friends, or even strangers, take a moment to ponder the wonders of calculated chance. Reflect on how closely we share these fundamental aspects of life. Just beneath the surface of everyday experiences lie surprising correlations, waiting to be discovered. The birthday paradox invites us to think critically about our assumptions regarding randomness and chance. It offers a glimpse into the underlying nature of connections and coincidences amongst people. The beauty of mathematics and probability is that it turns seemingly mundane ideas into intriguing revelations that can reshape our understanding of the world. In conclusion, this phenomenon serves as a reminder that you might not be alone in your experiences. At any moment, surrounded by others, there is a substantial probability that you are sharing more than just the air you breathe. This realization can foster a sense of unity and shared existence as we acknowledge the magic inherent in the very structure of human connections. Cantor was a mathematician from the 19th century whose groundbreaking work changed how we perceive infinity and set theory. Picture yourself standing at the edge of a vast ocean, looking out at a horizon that stretches endlessly. Infinity can feel similar, vast, perplexing, and full of possibilities. But what if I told you that not all infinities are created equal? This was the trailblazing insight that Cantor brought forth. Cantor introduced the concept of different sizes, or cardinalities, of infinity. To grasp this idea, let's start by considering the set of whole numbers: 0, 1, 2, 3, and so on. This set continues indefinitely. We will never reach its end. Now, in comparison, think about the set of all real numbers. These include whole numbers, fractions, and irrational numbers, such as pi or the square root of 2. This set also stretches infinitely, but Cantor showed that it is actually a larger infinity than the set of just whole numbers. To illustrate this, imagine pairing up each whole number with a real number. At first glance, it seems like you could match each whole number with a unique, real number. But Cantor employed a clever method, known as diagonalization, to prove that there are more real numbers than whole numbers, no matter how you attempt to make the match. Imagine creating a list of real numbers between 0 and 1. You might start with 0.1, 0.2, and so forth. However, Cantor's diagonal argument demonstrated that even if you believe you have listed all these numbers, there is always a way to create a new number that is not on your list. By changing the nth digit of the nth number in your list, you can construct a number that differs from every entry on your list. This means that, despite your efforts, you will never exhaust all the real numbers. This discovery led Cantor to define two specific sizes of infinity: the countable infinity of natural numbers and the uncountable infinity of real numbers. Countable infinity refers to any set that can be listed in a sequence, like the numbers we just discussed. You can count them one by one. Uncountable infinity, on the other hand, cannot be matched in the same manner. It is a higher level of infinity. Cantor's findings were revolutionary, sparking debates and discussions across the mathematical community. His work challenged long-held beliefs about number theory and laid the foundation for modern mathematics. Some mathematicians were skeptical and resistant to his ideas. They found it hard to accept that such abstract concepts could truly exist. However, like any great pioneer, Cantor persevered, sharing his ideas with unwavering conviction. As time passed, Cantor's theories gained more traction, leading to fascinating implications for mathematics. His work opened doors to various areas such as set theory, topology, and even computer science. The notion of different sizes of infinity has since permeated various fields, influencing philosophers, logicians, and scientists. Think about infinite sets in nature. For example, consider the vast number of stars in the universe, or the myriad forms of life on Earth. While the count of individual species may be finite, if we think about the essence and connections of existence, we touch on threads of infinite possibilities. Just as Cantor distinguished between levels of infinity, we can find that the connections of existence can vary in depth and complexity. Cantor's work also poses intriguing questions about the universe itself. The cosmos is not just a collection of stars or galaxies. It is an intricate tapestry of events and possibilities. Each moment, another thread is woven into the fabric of reality, leading to the realization that the universe is a dynamic system, rich with diversity and endless potential. In addition to philosophical discussions, Cantor's ideas have significant implications within mathematics itself. Consider the elegant structures of calculus, set theory, and even computer algorithm. The concept of infinity informs how we think about limits, sequences, and continuity. These principles have transformed mathematics from a mere tool for calculation into a profound lens for understanding the world around us. Cantor was not just a mathematician. He was a visionary who dared to see beyond the apparent limits of his time. His exploration into the nature of infinity invited others to think deeply about the universe. Through his groundbreaking work, Cantor has inspired generations of mathematicians to delve into abstract concepts with curiosity and determination. The exploration of infinity is not confined to mathematics. It can invoke wonder and stir the imagination, just like gazing into the night sky, wondering about distant galaxies. The idea of infinite sets opens up realms of thought. The possibilities of existence stretch beyond our comprehension, inviting us to ponder what lies beyond the confines of our understanding. Cantor's legacy reminds us that curiosity often leads to revelations beyond the ordinary. His commitment to his ideas, despite challenges, demonstrates the importance of open-mindedness in the pursuit of knowledge. By embracing abstract concepts, we open the door to new understandings and possibilities that can reshape our perspectives on life and reality. In the grand tapestry of mathematics, Cantor's revolutionary ideas remind us that there is always more to explore, always more to understand, and always more infinite possibilities awaiting our discovery. Just as he inspired entire generations, may we also find inspiration in the vastness of ideas that stretch beyond what is immediately visible. The exploration of infinity is a journey, one that invites creativity and wonder into the realms of thought and imagination. Cryptarithms are fascinating puzzles that engage the mind in a playful yet challenging way. These puzzles utilize letters to represent digits in arithmetic equations, creating a unique blend of mathematics and wordplay. Imagine an equation where traditionally you would see numbers replaced by letters, prompting you to decipher the language of numbers hiding behind the alphabet. Consider a classic example. The equation send more H money. In this puzzle, each letter corresponds to a unique digit from 0 to 9. Your task is to figure out what digit each letter represents. For instance, if SH9 equal 5, NOK 6, D2 7, M1 OCOT 0, the equation holds true. The challenge lies not only in the arithmetic, but also in the logical reasoning required to unlock the mystery of each letter's value. At first glance, it may appear to be a simple replacement task. However, the beauty of cryptarithms lies in their requirement for creativity and deduction. You must consider various combinations and how they fit together to satisfy the equation, all while ensuring that no two letters can represent the same digit. This restriction adds complexity and depth to the puzzle that makes it more than merely a substitution of characters. One of the most exciting aspects of these math puzzles is the wide variety of problems available. They can range from straightforward equations to intricate challenges that require extensive trial and error. Some cryptarithms use only a few letters, making them more manageable, while others involve longer sequences that test your patience and skills. Each variety presents an opportunity to exercise not just logical thinking, but also intuition and perseverance. To get started with cryptarithms, you might want to keep a few strategies in mind. Firstly, analyze the structure of the equation. Identify which letters are at the beginning of the numbers. Those cannot be zero. Remember that the first letter of each number represents a non-zero digit. This insight helps narrow down possibilities, giving you a stronger foundation to work from. Next, look for patterns in the equation. Sometimes, certain letters repeat, which can provide clues. For example, if you see the letter E appearing multiple times, it might represent a digit that adds up coherently within the context of the whole equation. Also, observe how the arithmetic works. Carryover values can create dependencies between letters that lead to further deductions. Collaboration can also enhance your experience with cryptarithms. Sharing ideas and insights with friends can spur new realizations that you may not have considered on your own. Discussing different approaches to the same puzzle can reveal a wealth of strategies and techniques for tackling cryptarithms effectively. Furthermore, engaging with online communities dedicated to puzzles could introduce you to an extensive library of cryptarithms at various complexity levels. You can find forums, websites, and even apps that host challenges, each presenting a new riddle waiting to be solved. This not only keeps the experience fresh and exciting, but also connects you with other puzzle enthusiasts who share your passion. As your skills develop, you might create your own cryptarithmic puzzles. Designing a puzzle involves choosing an arithmetic operation and creating a meaningful equation that can be expressed with letters. This creative exercise allows you to think like a puzzle maker, considering how others will interpret and solve the challenge you've designed. Cryptarithms also have a historical background that adds depth to the experience. The concept has intrigued mathematicians and puzzle enthusiasts alike for centuries. Famous mathematicians, such as Leonhard Euler, explored these kinds of puzzles, contributing to their recognition as a legitimate mathematical exercise, rather than just a playful pastime. In addition to just being an enjoyable mental workout, cryptarithms encourage various cognitive skills. They enhance logical reasoning and improve problem-solving abilities. When faced with a cryptarithm, your brain actively engages in recognizing patterns, testing hypotheses, and applying mathematical rules in creative ways. Beyond personal satisfaction, solving cryptarithms can instill a sense of accomplishment. Each completed puzzle offers proof of your logical prowess and perseverance. The joy of uncovering the answers, while practicing patience and focus, enriches the overall experience and leaves you feeling accomplished. Cryptarithms can also serve as an excellent tool for teaching math concepts. Educators often utilize such puzzles to teach students about numbers, operations, and logical reasoning in an engaging format. Children and adults alike can benefit from the skills developed through working with these problems, making learning both fun and effective. Ultimately, cryptarithms are a delightful way to stretch your cognitive muscles while diving into the intriguing world of numbers and letters. They transform simple arithmetic into elaborate puzzles, requiring creativity, logic, and persistence. Whether you are a seasoned puzzle solver or new to the concept, the thrill of cracking a cryptarithmic code awaits you. Dive into the world of letters and numbers and find the satisfaction of untangling their hidden relationships. Unravel the mysteries and let the adventure begin as you discover the beauty of mathematical puzzles filled with intrigue. Each letter, each number, brings a new layer of complexity and enjoyment, inviting you into a world where logic reigns supreme and creativity knows no bounds. The Sierpinski Triangle is a fascinating mathematical figure that captures the imagination with its striking simplicity and deep complexities. This fractal, named after the Polish mathematician Sierpinski, showcases the concept of self-similarity. a principle where a shape can be broken down into smaller versions of itself. It serves as a remarkable example of how intricate patterns can emerge from simple rules. To understand the Sierpinski triangle, imagine starting with an equilateral triangle, perfectly balanced and symmetrical. This is your first step into a world where geometry meets artistry. Now, take a closer look at that triangle. The Sierpinski triangle begins to take shape when you divide this larger triangle into 4 smaller equilateral triangles, each one smaller than the original. The process continues as you remove the central triangle, leaving a striking arrangement of 3 triangles at the corners. But the beauty does not end there. The magic truly unfolds when you repeat this process on each of the remaining smaller triangles. Each time you create these smaller triangles, the structure retains its overall triangular form, demonstrating self-similarity. It's mesmerizing to realize that as you continue this iteration infinitely, every scale reveals the same triangular pattern, endlessly repeating within itself. This concept invites us to explore not just mathematical concepts, but also philosophically deep ideas about infinity and the nature of reality. The Sierpinski triangle invites questions about space, dimension, and perception. As you visualize it, you might wonder how an object can possess so much complexity from such a simple beginning. In practical terms, Sierpinski's work also has applications beyond mere aesthetics. It appears in various fields, including computer science, nature, and architecture. For instance, some structures in nature display fractal-like behavior, from the branching of trees to the way coastlines form. The Sierpinski triangle embodies a bridge between mathematics and nature, leading to an appreciation of how abstract concepts manifest in the environment around us. Exploring the Sierpinski triangle can be an enlightening experience. Imagine the process visually, watching the triangles form and reform, each iteration creating a new pattern, while each smaller version retains the essence of the original. This interplay of shapes fosters a sense of harmony, demonstrating how simple geometric principles can lead to stunning visual outcomes. The beauty of the Sierpinski triangle resonates through art as well. Many artists have drawn inspiration from its structure, creating intricate designs and sculptures that capture its essence. By incorporating this magnificent fractal into artworks, they celebrate the intersection of mathematics and creativity, showcasing how 2 seemingly different worlds can collaborate. Additionally, the Sierpinski triangle serves as an excellent teaching tool in mathematics classrooms. By engaging students in hands-on activities that involve creating their own Sierpinski triangles, educators can illustrate concepts such as geometric constructions, patterns, and recursion. These activities make abstract mathematical ideas more tangible and relatable, inviting learners to explore their creativity while reinforcing core principles. As you've journeyed through the Sierpinski triangle, consider its many layers. Beyond its mathematical properties, it evokes a deeper appreciation for the world of patterns, symmetry, and beauty found in both nature and art. Each time you observe the triangle, whether in a drawing, a sculpture, or in nature, it beckons you to reflect on the infinite complexities that lie beneath the surface. Through the lens of the Sierpinski triangle, we come to realize that complexity and simplicity are often 2 sides of the same coin. What may seem simple at first glance can reveal profound insights upon closer inspection. Its iterative nature aligns with many aspects of life, where small changes can lead to immense transformations over time. In exploring the Sierpinski triangle, we uncover not only a geometric marvel, but also an enduring symbol of creativity and exploration. It encourages us to look beyond the ordinary, to recognize patterns in the world around us, and to celebrate the beauty that emerges from the synthesis of mathematics and art. Whether you're observing its form on a piece of paper or through the lens of a digital screen, the Sierpinski Triangle remains a testament to the elegance inherent in mathematical concepts, forever inviting curiosity and wonder. So the next time you encounter this triangle, remember its journey from a simple geometrical shape to a complex, endlessly repeating fractal. It's a reflection of how beauty and complexity are interwoven in the fabric of our understanding, inviting us to explore, create, and appreciate the intricate world we inhabit. And while it may be grounded in mathematics, the echoes of the Sierpinski Triangle extend far beyond numbers, inviting us to ponder the nature of existence and the patterns that shape our lives. The law of large numbers is a fundamental concept in probability and statistics, and it provides a fascinating insight into how we can predict the behavior of random events over larger sample sizes. To illustrate this principle, let's consider an everyday example: flipping a coin. When you flip a coin a few times, you might get heads 3 times and tails only once. At this point, it may seem as though the coin is biased toward heads. But what happens if you continue to flip the coin, say, 100 or 1,000 times? As the number of flips increases, the proportion of heads and tails will begin to stabilize. If the coin is fair, you would find that roughly half the flips result in heads and half in tails. This behavior illustrates the law of large numbers perfectly. This law states that as the size of a sample increases, the sample mean will get closer to the expected value of the population mean. To understand this better, think of a more complex scenario involving dice. Suppose we are interested in finding out the average outcome of rolling a 6-sided die. If you roll the die just a few times, you might end up with an average that is skewed. For instance, you might roll a 4 once, a 2 twice, and a 5 once, giving you an average far from the expected value of 3.5. However, if you were to roll the die 1,000 times, the average outcome will likely hover around 3.5. This is because the larger the number of rolls, the more balanced out the extreme outcomes become. The law of large numbers assures us that randomness averages out over time, bringing us closer to the true expectation. The principle is not just applicable to dice and coins. It can be observed across numerous fields, from economics to science to sports analytics. For instance, in business, a company may launch a new product. Initially, sales could vary widely due to many unpredictable factors like consumer interest, marketing effectiveness, and seasonality. However, over the course of several months, as more data about sales is collected, the company can get a clearer picture of the product's average sales performance. This ultimately guides future decisions, reducing uncertainty. In the context of sports, consider a basketball player who has an inconsistent shooting performance. In a handful of games, they might miss a significant number of shots, leading fans to question their abilities. But as the season progresses, with more games played, over time we are likely to see an average shooting percentage that reflects the player's true skill level. The more games played, the more this average can be trusted to represent that player's overall performance. Another fascinating application can be found in the field of medicine. Researchers conducting clinical trials might start with a small number of participants. Given the small size, the results could be influenced heavily by a few outliers, such as an unexpectedly effective response from one participant. However, as the sample size grows to include many participants, the average efficacy of a treatment becomes clearer and can provide more reliable insights into how that treatment might perform in the general population. Psychology and social science studies also frequently rely on this principle. Let's say researchers want to investigate the average number of hours people spend on their smartphones each day. A survey of just 10 individuals might show a wide range of results influenced by personal habits and lifestyles. In contrast, a survey of 1,000 participants will offer an average that accurately reflects broader societal trends. Despite its intuitive nature, the law of large numbers can lead people to misunderstandings, particularly in situations where randomness is at play. For example, someone might believe that, after flipping a coin for 6 times with 5 heads, the next flip ought to favor tails because it seems overdue. This is a classic fallacy known as the gambler's fallacy. In reality, the coin has no memory. Each flip is independent of the others, and the probabilities remain constant. The law of large numbers reinforces the idea that while individual outcomes can be unpredictable and vary widely, the aggregate of random events behaves predictably over time. It provides a comforting glimpse into the inherent order within the chaos of randomness. In conclusion, the law of large numbers is more than just a mathematical concept. It's a powerful principle that helps explain many real-world phenomena. From how we interpret sports statistics to how we analyze financial markets and medical trials, it underscores the importance of sample size in understanding averages. The deeper you delve into this principle, the clearer it becomes that while randomness dominates in the short term, patterns emerge and stabilize as we look across larger samples. Observing this balance allows us to make more informed decisions and predictions across various fields, reflecting the quiet harmony that underlies the seemingly chaotic world of chance. In the mid-18th century, a groundbreaking problem emerged from the city of Königsberg, Prussia, now known as Kaliningrad, Russia. This city was characterized by its distinct geographical layout, with the Pregel River winding through it, creating various islands connected by a series of bridges. The fascinating question that arose was whether one could devise a route that would allow a person to cross each of the city's bridges exactly once and return to their starting point. This question, simple yet profound, caught the attention of a prominent Swiss mathematician named Leonhard Euler. In 1736, Euler approached this problem, which would lay the foundational concepts for what we now recognize as graph theory. His innovative analysis opened the door to numerous applications in fields ranging from computer science to urban planning. Euler started by representing the city's layout as a graph. He treated the landmasses as nodes or vertices, each of the 4 landmasses representing a point in the graph. The bridges that connected these pieces of land were seen as edges or lines connecting the nodes. By doing this, Euler transformed the physical layout of the city into a more abstract mathematical representation, allowing for logical reasoning to unravel the complexities of the problem. To understand whether such a path across the bridges existed, Euler established specific criteria based on the connectivity of these nodes. He theorized that if a person could traverse every edge without retracing their steps, the pivotal factor would be the degree of each vertex. In graph terminology, the degree is defined as the number of edges connected to a vertex. If a vertex has an even degree, it means that there is a paired number of edges leading into and out of it. On the other hand, a vertex with an odd degree suggests that one edge leads into it without a corresponding edge leading out. Euler realized that for a route to cover every bridge exactly once and return to the starting point, all vertices must have even degrees. However, If the total number of vertices with odd degrees is exactly 2, then an alternate path could commence at one odd vertex and finish at the other. In the case of Königsberg, Euler discovered that 4 vertices represented the landmasses of the city, and of these, 3 possessed an odd degree. Therefore, it was impossible to devise a route that crossed each bridge exactly once. The implications of Euler's findings were far-reaching. This seemingly trivial exploration of bridge crossings introduced the concept of Eulerian paths and circuits. An Eulerian path is a trail within a graph that visits every edge exactly once, while an Eulerian circuit connects back to the original starting node. Euler's work influenced many areas within mathematics and beyond, as graph theory became a critical tool in understanding networks, whether they be transportation systems, social networks, or communication pathways. Euler's bridges problem also sparked the interest of other mathematicians and thinkers, leading to further investigations into what characteristics define traversable graphs. The study of these connections soon broadened into various fields such as topology, combinatorics, and even computer science, where algorithms derived from Eulerian paths are employed to optimize routes and manage data networks. Beyond formal mathematics, the cultural references to Euler's bridges have persisted through time, with the intrigue of puzzle solving and logical reasoning captivating minds in various realms. People often enjoy the challenge of navigating mazes, seeking optimal paths in games, solving riddles, or even finding the best route for delivery services. The principles derived from Euler's examination remind us that curiosity about the simplest questions can often lead to expansive realms of understanding. In addition to the specific case of the bridges in Königsberg, Euler's approach provides insight into how we conceptualize and visualize complex relationships. The transformation of physical structures into abstract entities showcases the elegance of mathematics in illustrating real-world phenomena. As we journey through modern cities filled with bridges, roads, and networks, the ideas behind Euler's problem remain relevant, highlighting the interconnected nature of our environments. Ultimately, Euler's exploration of the bridges in Königsberg exemplifies the beautiful blend of intuition and logical reasoning that characterizes mathematics. It serves as a reminder that even the most straightforward questions can lead to profound discoveries, reshaping the way we perceive not only mathematics, but the world around us. Through Euler's legacy, we gain not just an answer to a historical curiosity, but a lens through which to explore the interconnections that define our surroundings in a complex, ever-evolving landscape. So next time you cross a bridge, take a moment to reflect on the journey of thought that has woven countless pathways in the fabric of our mathematical understanding. The story of Euler's bridges problem continues to resonate, inviting us to ponder our pathways, both literal and abstract, and to celebrate the enduring quest for knowledge in every corner of existence.